right, good morning, everyone. Welcome to the sessions on parallel and asynchronous programming with streams and completable future. My name is Venkat Subramaniam. We're going to talk about two really exciting and very different concepts available to us in Java. And I want to talk about just a little bit for a few minutes about some of the challenges we normally face with concurrent programming. And then, of course, jump into two different ways of solving the problem. The examples I'm going to show you here will eventually be uploaded to my website. If you're interested, you can download them from the downloads link. It doesn't exist there today, but by the time tomorrow, let's say about this time, if you go to the site, you should be able to download all the code examples that I'm going to provide you here. So let's get started. Well, one of the things that we normally do is we want to improve performance in applications. There are times when the goal is to improve performance. The time also is where we want to make sure the application has a good responsiveness. So typically what we do to make these two things happen is we turn towards programming concurrency or multi-threading. Well, as it turns out, one of the really nice things about Java was right from the day one, we had ability to do multi-threading and concurrent programming. Well, unfortunately, though, if you really look at it, we have been looking at solutions after solutions for this over the past 20 years, and almost every time we think we have a handle on it, it slips away. Well, if you step back in time to think about what we did in the very first release of Java, we had the ability to create threads. And we eventually realized that was probably not the best thing to do. Creating threads is not the most optimal thing to do. Maybe we want to have really pool of threads. So Java 5 introduced the executor services. And then, of course, we realized that potentially causes pool-induced deadlock. Then, of course, Java 7 introduced the fork join API. Well, we can see that we almost solved every single problem only to create more problems. And so looking at it, how do we really program concurrency? Well, as it turns out, if we start creating arbitrary threads and we start managing those threads, we end up with quite a number of trouble over time. When I used to program multi-threading in Java, I had this suspicion that it's almost impossible to do concurrent programming in Java and get it correct. And I'm going to say probably the most scariest book for any Java programmer is Brian Getz's book on Java concurrency in practice. So before I read that book, I used to think programming concurrency was really hard. And after reading that book, I was convinced that programming concurrency is absolutely hard. And that is one of the real challenges of this is it's incredibly difficult to really get all the things wrapped around in our head and do it properly. Well, thankfully, Java has some solutions to tame that beast so we don't have to struggle so hard with it as we start programming concurrency. So what I'm going to do here is to talk about really two parts in this particular presentation. One is about the parallel streams library, and the other is the completable future. So we'll talk about the parallel streams to begin with, and then we'll take a short break after that, and then we'll continue talking about the completable future right after that in this presentation. So when it comes to nature of the problem, we have a lot of times we have computations we want to perform, and we want to perform with speed, we want to perform with ease, we want to perform maybe to improve responsiveness, whatever the nature is. There are two kinds of solutions we can seek when it comes to programming with multi-threading. One is where we may have a collection of data, and we want to really process that collection of data. In a lot of different languages, we call these as arrays and parallel array solutions. So when you have array of data, or using the word array very loosely here, when you have a collection of data, you want to be able to process that collection in parallel, and that's exactly where the parallel stream fits in really nicely. On the other hand, if you don't have a collection of data, but you just have a problem, and you want to divide and conquer this problem. So maybe this problem can be split into a smaller part, and then once you split into a smaller part, you can make a decision at this point. Do you want to continue splitting into smaller part, or maybe it's really small enough that you can actually solve it right now? That could be another way to think about divide and conquer. If you're looking at a divide and conquer strategy, a parallel stream doesn't quite fit into it because you may not even have a stream to begin with. Well, that's where asynchrony can come and really help us to really set this off in motion in asynchronous manner. You go off and do your work, and then that particular asynchronous task you set either can solve the problem and get you a result back, or can split further and then eventually get the result back to you. That's where the ability to do the splitting and then putting it back together can come in. And those kinds of problems really fit nicely for completable futures, as we will see a little later on. So with that said, let's switch our focus to talking about parallel streams itself. But before we talk about parallel streams, let's talk about one thing we have been doing really well moving forward. This is going to change fundamentally how we approach problems and how we solve them. Well, in the past, we wrote code in the imperative style. Just as an example, let's say for a minute, if I have a list of numbers 1 to 10, and I want to really total, let's say, all the even numbers in this collection, double of the even numbers in this collection, the real boring and more complex way to do this, even though it's familiar, is to really start saying result equal to 0, and then start doing a for loop. Maybe a for I equal to 0, and then start wondering how to set the bounds. Or maybe we can say, given an element in numbers, I want to start saying that if element mod 2 is equal to 0, well, then maybe I want to really compute result is plus equal to e times 2. And then, of course, I can bring back the results when I'm done with this and display the result. Well, this, of course, as we know, is the imperative style of programming, which we've been doing for a very long time. But this is inherently more complex. In fact, I will give you a challenge. When you get back to work, do a grep on your source code for the number of times we use the for, and it's going to be really scary. And this is a very traditional for loop and maybe occasionally while loop we have been doing. But Martin Fowler has a beautiful blog post, and his blog post is called Collection Pipeline Pattern. And the collection pipeline pattern, a blog post by Martin Fowler, and if you look at this blog post, he makes a good claim that we are going to be fundamentally shifting the way we start writing code. So what we will do instead is we'll say numbers.stream, where that becomes an internal iterator. And then we're going to say, in this case, filter given an element mod 2 is equal to 0. And then we perform a map to int in this particular example. And then we can double the value given to us. And then finally, we can perform a sum operation on that particular object. So this really becomes a very nice, compelling collection pipeline pattern as we move forward. And as a result, this really removes the complexity that's in code and makes the code a lot more easier to understand, easier to maintain. But it's not just the beauty of the code that really matters. I'm going to say, but this is something that really I'm beginning to realize more and more, and we really want elegance. So no doubt about it, right? So elegance is nice. To look at the code and say, oh, it's beautiful is nice. But elegance in the absence of efficiency is no good. So we cannot say, my code is beautiful and walk away. And elegance in the absence of efficiency is absolutely no good. And that's one of the beautiful things about Java is, Java did not just give us elegance when it comes to having the functional style of programming, they also gave us efficiency. And one of the beautiful things about this elegance is, it's also a nice pathway to gain efficiency as well. And that's one of the real benefits we begin to reap at this point. So this function pipeline pattern becomes very compelling moving forward. Now, one of the things we know, of course, about the collection pipeline pattern in Java is that it is fundamentally lazy evaluation. It will not go off and do work unnecessarily, and it will only do enough work to get things away. But of course, because the function pipeline pattern is elegant, because the functions we create don't have any side effects, they are pure functions, such functions are easy to parallelize as well, and that's the aspect we want to focus on in today's, at least the first part of the presentation. But as we do, I will also swing back to this efficiency and laziness later on, and we'll address that and see how that's going to matter as we go through. So most fundamentally, this collection pipeline pattern is one of the most significant things we're going to see moving forward in generally in programming, and especially in Java, is we're going to start beginning to use this collection pipeline for a greater fluency of our code, expressiveness of our code, elegance of the code, but also for efficiency as well. So we can go from the imperative to the functional style of programming where the code becomes a lot more declarative. But some of the benefits of this pipeline pattern are, I mentioned that it's efficient, it's easier to read, easier to understand, easier to work with. It is also removing the accidental complexity in code, but one of the charming features is it is easier to parallelize. So if I want to really parallelize my code, how do I go about parallelizing such a piece piece of code. If you write a code which is imperative in nature, and somebody comes to you and says, let's make it faster, let's make it concurrent, you're going to find the nearest door out. And this is one of the things I love about what Java 8 has done, and we cannot simply take this lightly. So let's talk about the dark days before Java 8. And how was the past? The past was the following. The structure of concurrent code was very different from the structure of sequential code. And this was a nightmare, right? So your sequential code was simple. Your sequential code was pleasant. And when you wrote sequential code, when you walked to work, you smiled at everybody. And everybody had a good time at work. And one day they told you, you need to improve performance, and you started putting multi-threading into your sequential code, and that's the last day anybody smiled at each other. And what did you do? You spent time at work debugging this code throughout the night. And there are days when you probably left the computer still blinking on the debugger, and the next morning you come back and you realize that the pizza you left on the table is on the keyboard now, and you just move it away and start debugging further. And then what did you do after trying this for a while? You realize this is not going to win at all, because every time you touch the piece of code, more bugs keep creeping in. And one morning you decided you're done with it, so while you're debugging the code, you applied for the other job. That's called concurrency, right? And you said, I'm done, I'm not going to do this anymore. Well, that's really hard because the structure of the code is so wildly different. It's very difficult to debug. It's very difficult to reason the code. And all the effort you put into making the reasoning in sequential is just gone. Well, the beauty is, for the very first time in a long time, Java 8 did something absolutely phenomenal. So this is the beautiful present. And what does the beautiful present look like? And the beautiful present looks like the following, right? Thanks to streams, we can claim that now the structure of concurrent code, and this is something we cannot just take lightly at all, is the same as the structure of sequential code. And this is remarkable because we don't have to go through an enormous pain in order to do this. So looking at the code we have in our hands right now, if you notice in this particular example, I have the code running sequentially right here and produces the result. But if this were a very large collection, or if the computations here were time-consuming, I don't have to put too much effort to make this code concurrent. All I have to do simply is change this to a parallel stream right there, and now that runs in parallel. That's one option. Alternatively, I can also do something else. I can simply say parallel here and then run it in parallel as well. So notice the structure of sequential code and the structure of concurrent code are exactly the same. And to me, this is a very fundamental feature of streams, is that the structure is exactly the same, and that takes away so many problems from our shoulders. So what I'm going to say here is that Java 8 made parallelism a master switch, at least in this very restrictive context. So parallelism is a master switch. Well, why is it a master switch? And the reason I call it a master switch is I often have developers ask me, well, if it is so easy to do and if it's so simple to work with, why didn't they make it parallel all the time? And the reason is very simple. They gave this master switch, and if you really look at the documentation, there's a fine print that has the word think in it, because they want us to think about turning on the switch, and before you flip that switch, you want to think several times. It's easy to parallelize, but doesn't mean we have to really parallelize. We have to ask the question, does it make sense to parallelize or not? So let's talk about these things in here. Let's start with the sequential execution, and then we'll go towards the parallel from there. So let's take a fairly simple example here and work with it. Let's take a collection of, let's say, these 3 numbers and play with it. I'm going to create a little silly little example to illustrate these things. So we'll say over here is static, let's say transform. And in this transform function, all I'm going to do simply is to take a number And for now, I'll simply return the number itself. Not a whole lot of transform in reality. But this gives us an ability for us to understand how the code works without having to think through all these computations. So what I'm going to do is numbers.stream, and then I'm going to then say, of course, perform a map operation where I'll call the sample and perform the transform operation. And then we'll say for each and system.out, and we'll just print it. So in this example, as you can see, it's a very little operation that just transforms the values into the same value and just prints it out. But let's talk about the transform itself. In this example, we are doing a sequential execution, but how do I turn this into parallel? Well, there are two options, like I mentioned, that are available to turn this into parallel. One is, if you are at the source of the stream, you can say parallel and perform the conversion to a parallel stream. This is very useful if you are the creator of the stream itself. Then this is clearly an easy way to do this. You can just say parallel stream and then execute that in parallel. And you can see the output sequence is not the same. That's a little proof that it's running in parallel. But on the other hand, if I had said stream over here, you can see that the sequence is still the same as in the original. So you can see that it's, gives us a hint that something is happening a little different at least. So this is one way to really achieve it. But what if you are not the source of the stream, if you're not the author of the stream or the creator of the stream, what do you do then? So in this case, for example, you might have a function that says, for example, work with stream, where the work with stream may receive a stream, let's say in this case an integer, stream as an argument. Well, in this case, you could say stream.map, and you can perform some operations on it. But if you are not the creator of the stream, obviously you cannot do parallel stream at this point. That's when you can say dot parallel, and then as a result, as a person receiving a stream, you can decide to run the stream in parallel because you don't have the luxury of saying parallel stream at this point. So you can pick and choose what may make sense. If you're the source of a stream, use parallel stream. If you're not a source of a stream, but you are receiving a stream and you want to make it parallel, then use the dot parallel, and you can go back and forth. In fact, this is even another benefit you get out of this as well. I'm doing this on my project at this time. We have a stream, but we don't know whether to run it in parallel or to run it sequentially, because that depends on a lot of different things. So we may even receive a parameter to our function. For example, you may say comma, a Boolean, and then you could say run parallel. And then, of course, I can come in here and say there are several ways to do this, but here's one example. If it is run parallel, I can then say stream over here is equal to stream.parallel, or you can create another variable rather than changing the input given to you. So this could be and then you can start using that stream. Well, it depends on whether the run parallel was true or false. You may decide to run it parallel or sequential. Like I said, there are multiple different ways to alter this. This is just one trivial example of how you can achieve it, but I would definitely give a different name than changing the input and then use that variable throughout the code after this. So we saw why we would use maybe a parallel stream versus a parallel call, but there are a few things we have to be very careful about when it comes to these things. So we can go from stream to parallel stream, but let's observe the thread of execution just a little bit to get a feel for what thread is going to execute this particular call. So to understand this, let's go ahead and put this back into our regular sequential stream, but in the transform function, let's go ahead and output, let's say, transform, and then we will go ahead and output, let's say, thread.currentThread right here. When we do this, of course, we want to know what thread is executing all these calls. And then when we run it, we can see that all this is doing is running it in the main thread. And that's, of course, no surprise at all, because we're doing this sequentially. But on the other hand, if I were to go ahead and make this a parallel stream, whether I make it a parallel stream right there or do a parallel right here, then of course we notice that it's no longer running in the main thread. It actually runs in a combination of different threads. Sometimes it's a main thread, sometimes it's the thread from the fork join pool. We'll understand why that is just a little bit later, but you can see that it's actually varying the different threads that's running this, which is definitely a good news as well. So we can see how this is running in parallel. So we can change it and see that the thread of execution is actually different. But having said that, though, we need to be a bit careful about a few different details when it comes to this. Now, if you may wonder, if there is a call to parallel, maybe then there is a call to sequential as well. And it turns out there actually is. So in this case, I made it parallel, but then I turned it sequential. And of course, now it's running in sequentially. But this begs the question, maybe this gives us a little idea. It says, aha, look at how beautiful this is. I can run the map in parallel and then run the for each in sequentially. Unfortunately, that's not really true. So in this particular case, the last one actually wins. So if your last call is sequential, then the entire pipeline runs sequentially. If the last call is parallel, then the entire pipeline runs in parallel. So notice, even though we said parallel here, or you could have said parallel stream when you created it, even though the parallel appears before the map and the sequential happens after the map, the transform is not going to run in a parallel as a parallel stream. The entire stream is going to run sequentially at this point. That is the nature of how this actually is built. So you're not really making parts of the code run parallel and parts of the code. So if you have this vision that I will have a pipeline, but segments of the pipeline will be parallel and segments of the pipeline will be sequential, that's a nice vision, but that's not what streams do for us. So the entire stream is either parallel or the entire stream is sequential, depending on what we configured as the last one or what we started out with. So something to be a little bit careful about. But that brings up the question then, if we go back to this code here, I want to run this in parallel or run this in sequential. Let's comment out the output for just a minute. Run the code. You can see the output is 1, 2, and 3. Well, remember the given collection is an ordered collection. If this were a set and not a list, we know a set is unordered. When a set is unordered, there's no guarantee on the ordering, so streams will not pretend to try to impose an ordering on what is not ordered unless you introduce a method that requires ordering somewhere in between. So what is the stream's order? Well, the stream's order is whatever order it starts with or whatever order it's influenced in the midway. But on the other hand, when it comes to parallel, parallel does not impose any ordering, even if the original collection had ordering in it. So there's a good news and a bad news here, as you can see. When I run this code sequentially, the ordering is preserved because the list had an ordering, 1, 2, 3, and the result was 1, 2, 3, as you can see. In fact, let's go ahead and put this to our original collection of list of numbers 1 to 10. In this case, when I run this, you can see the ordering is 1 to 10. On the other hand, if we were to change it to a dot parallel right here, and in this case, of course, running it parallel, what does that do then? Well, there's no bet on ordering at this point. I'm just going to run this on the command prompt so we can actually see this a little bit easier. When I run this, you can see the ordering is completely different. It was 7681, but the next time I run it, it is 7985, and who knows what the ordering is going to be the next time, 7253. So we cannot guarantee what the ordering is. Well, there's a good news and a bad news. The good news is, if these computations were taking time to perform, you're not waiting for those computations to finish. You can start multiple computations at the same time, so you can get speed. But unfortunately, though, there's no ordering of the output. What if you go to a customer and say, I've got a good news and a bad news. I produce a report really quickly for you, but good luck, putting the pages back together. That's not going to invite good customers for us back to us, because what's the point in producing such a result so fast that the output is completely jumbled up? Well, the key here is there are ways to really control the ordering. So how do you execute the operations in a certain order? Well, the way to really execute this in a certain order is there are a few methods that can impose ordering for you. Now, there are some methods that will quietly impose order without you even knowing or telling it. There are other methods that will impose order only when you specifically use methods with a certain name. Clearly, in this particular example, we'll see a few more later on, for each is not ordered, and as a result, there's no guarantee on the ordering. On the other hand, given the scenario as we just saw, when there is absolutely no ordering being imposed, what if I go back here and say for each ordered over here? When I say for each ordered, notice that it will impose the ordering. So no matter how many times I run this, it is going to have exactly the same ordering. Let's not confuse the for each ordered with sequential execution. It is not sequential execution. It is just serialized in the order in which it is going to execute. Just to illustrate this point, let's go back to this example and look at it slightly differently. Rather than calling a println, let's call it as sample, let's say, print it. Well, print it is going to print out the result for us. So we'll create a print it method right here. So we'll call this as void print it. And then it takes a number, and all it's going to do is simply output the number. Well, in this case, of course, it's going to output the number. Well, we're not going to see anything really different other than, just seeing the number again when we call the printed, and that's the printed is going to simply return that result for us. Well, that's great, but I want to really print out one other piece of data. When I'm printing the number itself, I'm going to go ahead and then say thread.currentThread, so we can actually see the thread of execution of the printed. Now, if I were to run this in sequence rather than parallel, it's no surprise that you will see that all of these are printing the number from the main thread, no doubt about it. On the other hand, if I were to put a parallel on this, notice that in this case, it is going to print, but the threads are not really the main thread. That is still running in parallel threads. But notice the sequence is followed. What really gets exciting in this case is, if I go back to this code now and print the current thread data right here, and along this we'll also print transform plus, let's say number plus, and then so we can actually see what number is being processed right now. But then we will go ahead and say over here, sleep.sleep, and give it about a second delay, if you will, so we can actually see, thank you. So we can see that in this case we have a second delay on this call, and so we can see that it's really going to delay this a little bit and execute this call, as you can see. If I give a 2-second delay, maybe it gives us a little opportunity for us to notice it. So when I go back and run this little code, you can see that the transforms already happened. But notice 4, 9, 7, 5, 3 was the sequence. 4 was done, and 9 was done, and 7 was done. 1 and 2 are coming much later in the game. But when you look at the output, though, you can see that they follow the ordering. So even though the code ran in parallel, it simply says, I am ready to do my part in my thread, but I'm going to wait until you finish your part in your thread, and then this can kick in and do the work. So that's why it is still concurrent execution, but an ordering is imposed on that particular execution in the terminal stage at this point. So these kinds of terminal operations can help us to impose ordering, which is very important in a lot of different cases. For example, in this case, you can see the for each ordered made a difference. But another place where the ordering is very important is when you ask for find first. If you ask for find first, you definitely want the first element that satisfies your expectations and predicates and whatever you provide. So the ordering is still important. You don't have a find first ordered. Find first is always ordered. So you don't have to say it at all. So find first will always give you the first element that meets that particular expectation. So there are certain methods that always impose ordering even when you run them concurrently, whereas other methods may require ordering by using a special flavor of those methods to get you that particular call. So that's basically about how we can control the ordering. But that brings up the question, what are the things I can do in parallel? Well, clearly, we can do filtering in parallel, which is really a nice thing. Because if I want to do filtering, why would I want to wait? So what does filtering do? Filtering says, given a collection of values, I'm going to cherry pick a certain values and drop other values. Well, the good news is, if I want to pick a certain value, I don't have to look for its left or right or other values. It is by the merit of that value, either I pick the value or I drop it. Well, in that case, I can simply do that concurrently. Given n number of values, I can concurrently decide if any of the values are something I should pick or not pick. I don't have to wait for doing that sequentially. So clearly, filter can run in parallel. Let's see if that's actually true in this case. So I'm going to go back here and say .filter, and then in this case, we'll say sample check right here. Again, this check is not going to do real check at all, but just for us to observe the values, we'll do the check. So in this case, we'll go ahead and call the check check method. This is going to be Boolean. And then, of course, there's going to be a check. And what am I going to do within the check? Well, I'm going to simply return, let's just say, a true value. But I'm going to go ahead and call this as a check. And I'll print the number and the thread information also so we can return it. So I'm doing a filter operation on the check. And then, of course, once I filter it, I'm going to simply print that result in the ordered fashion. If we go back and run this little code now, you can see again the filtering happened almost in here in arbitrary order. But then, of course, eventually the for each is ordered, so the filtering can happen in parallel too. That works really nicely. So filter can be in parallel, map can be in parallel. So we begin to think about this and say, is there something that maybe shouldn't be run in parallel? Hey, what about reduce? Let's understand what reduce is before we talk about what that really means. Well, in terms of parallelism. So let's go back to this example, remove all of this, and now let's talk about the reduce function. I'm going to call the reduce on the stream and say reduce, and I'm going to provide a value 0, and then I'm going to provide a total comma element, and I'm going to call a function called add, and I'll pass the total and element to it. Well, how does the reduce method actually work? Well, the reduce method is, by the nature of it, is going to, in this particular usage, it's going to reduce the collection into a single value. So if you had a collection, let's say 1, 2, 3, 4, and such, well, what reduce is going to do is, it's going to first start with what's called an initial value. Well, the initial value could be a value of 0, as we gave on line number 26, and then we take that and we pass it to some kind of an operation. The operation could be whatever that you call in here. I'll just put it as op, whatever the op means to you. Well, it's going to take this value and this value here, perform this operation, take the output, and then perform the operation one more time. And in this case, of course, it's going to send it off to this. And then, of course, then it's going to take this one here and then take the result of that, perform the operation. And then it's going to take the result of that and perform the operation. And it kind of goes on with the sequence until it's done with it and produce the result in the very end. So in a sense, what this is going to do in this example is we're going to take the value of 0, and the 0 is fed in as a total in the beginning. So remember, the initial value is the input to this operation. The current element in the collection becomes the second value to the operation, and the result of that is actually fed back in as a total in the next call. And the second element becomes the element. The result of that becomes the total, and the third element becomes the element, and then so on. So this becomes a operation where we keep marching through the elements. As we march through the elements, we take the result, and then we feed it back, and take the result and feed it back, and it just keeps moving forward like that. Let's take a silly example of how we could potentially use it. We got a room full of people here. What we could do is we could say, I want to perform, let's say, the total of everyone's age in this room, starting with the person on my far right. He's not smiling anymore. I'm not going to ask for your real age. So I'm going to send you a 0, let's say, initially. You take the 0, you total your own age with it, pass it to the person next to you. He takes his own age, adds the total given from his left, and passes it down. And we can just sit there and watch this value go through, and one row at a time. And what we eventually get from that last person up there, most likely is going to be an overflow, or otherwise we're going to get the result of it. And so as a result, that's going to trickle through. Hey, looks like that's a pretty darn sequential operation after all, because we have to just popping through every single value and perform the computation. Well, it kind of appears that way in the beginning, but we'll come back to this in just a minute. So what I'm going to do here is I'm going to say public static, let's say int add. We'll call it as total comma int element. And then in this case, I'm going to simply return, let's say, a result of this totaling. But what in the world is result? Result is equal to, we'll go ahead and say this is total plus element. And as a result, what I'm going to do here is output. Let's output total over here with the value, let's say, total. And then, of course, we'll also output, let's say, the element E with the value E. And finally, we will output result with the value, let's say, plus result. So as a result, we have those different things. So as a result, we're going to just output those values as we run through this, and you can see how that propagates through. Notice the 0, which is initial, and 1 produce a result of 1, but 1 became the input to total, and the result is 3 that became an input to total. You can see that output on the right side carry over to the left side. That's the feedback that we talked about. And the result is 55. Now, we can all agree to one thing. When you do an operation parallel, you'll be very happy if you get the result faster. But you should never get an incorrect result when you run parallel. If you want to run code really fast and you don't care about the result being really wrong, then you should go back and program in C++. But if you really, because that's where you care about performance and nothing else in that world, isn't it? But on the other hand, the correct result should be obtained and it should be faster as well. So how do we really do that? Well, in order to do this, we're going to say, what if it's going to be running in parallel? Well, let's go back to the example we talked about. I want to total the age of everyone in the room. Well, I can realize suddenly I don't have to do this sequentially. I don't have to start the value 0 here and the value trickle through the room and just sit there and just watch them until the cows go home. Instead, I can say, hey, folks, we have several rows in this room, and we also have several columns of chairs in this room. So for every segment in the room, we're going to take every row and let the people in every row do the totaling on their own row. So for example, the first row on my right side is going to do totaling in the same exact approach. And while the first row is totaling, the second and the third and the fourth row is going to do that. Similarly, in the middle section here, we're going to have people doing concurrently in each of the row, and so in that corner section as well. Now we can see we can have concurrent execution for every single row in the room, in every single column. But then what we can do is, at this point, the people on the very right side of each of the row are going to hold on to the data for the total of their own rows. Now we can turn around and run through this way, because this becomes a row of all the columns, and we can do a totaling. And similarly on this one and this one, then we can take these 3 values and combine them together. This, of course, makes sense when these operations can be combined in that way. So just because we can run in parallel doesn't mean it makes sense to run in parallel. It's got to make mathematical sense to do this based on the problem we have on our hand. But assuming we can do this, what would it do then? Well, let's take a look at this real quick before we go further. If I run this notice, that is the output we got. Just out of curiosity, how many rows of output did we have right now? That was about 11 rows. It doesn't matter how many times I run, it's always going to be 11 rows, because in this given example, with the same input, it'll always be 11 because we're going to have 10 elements. And remember, we are just hopping through every element. That's 11 computations overall to get the result through it. Well, with the final result being the 11th one. So that's kind of obvious. On the other hand, if I do a dot parallel on this, remember what we just said, we're going to take each of the rows and do the work at the same time. But what does it mean, rows, when it comes to the collection? Well, the streams internally have the ability to do things in parallel as well, and so they can start doing these computations in parallel. So as a result now, notice all I did was I turned on parallel on this. Now when I go back and run the code this time, you will notice there is a lot more number of lines in the output. Not only that, notice there's a total of 0 and 6, 0 and 4, 0 and 9. So you can see all these totaling happen, and then you can see the combination of those values come together. Good news, it is still 55 in the very end. But how many lines are we seeing in the output? Well, that was 20 instead of 11 this time. Who knows, what the value will be depending on the size of the input. But you can see that it actually did this in parallel as well. So what are they actually doing? Well, what they're doing is they're saying we don't have to really wait for this to be done sequentially. We could start off this one with, while this totaling is being done for this, we could start off this as well, and this as well, and this as well, and so on. But here also comes the good news and the bad news. Good news is reduce also runs in parallel. But we have to really understand what this is doing, because otherwise it'll be really a problem. So let's get back to this example one more time. Let's just look at it sequentially. When we run this sequentially one more time, notice given these input, the output is 55. Well, that is the value, no doubt about it. But I get this desire to not only total these values, but I want to total the values and add it to maybe yet another value. Like, for example, I want to total the age of everyone in this room, but I don't want to start with a 0. I want to start with my own age. So I'm going to put my age over here. So you don't believe it? Okay, so I'm going to start with my age in here and then start propagating that value down through the chain. So, when I typed this, somebody asked me, what is the base of the age? No, never mind that. Okay, so the point really is we can propagate through the chain and then have the total. Well, here's the good news. When I started with the 0, it was a 55. If I start with a 21, it's very clear it is going to be 76 no matter what. So that makes sense. But be careful though, this is not an initial value. This is a misguided view of the world if we think it's an initial value. So let's step back and ask, what is that value? So the value that you pass to reduce is actually, it's an identity value. So what is an identity value? Well, in the case of a sum, the identity value is a 0. No matter what you total with the no matter what you total with 0, you always get that value back. Similarly, in the case of a product, the identity value is a 1. No matter what you find a product with 1, you always get that value. So be very careful. This is an identity value. Why is that so important? Notice now, I put a 21, which is not an identity value. When I run this, it gives us 76. But unfortunately, if I go back and say dot parallel right here, then the result is no longer 76. That is all of a sudden some other value, which doesn't make any sense at all. So the moral of the story is, don't do this. So what is the thing we should do really? Keep in mind this is an initial value that we should give in here. So what is the right approach to do this? The right approach to do this is to say 0 here, and then when the result eventually comes out, then you do a plus 21, and it is okay to do this. So this is okay, not the other one. So notice we ran it in parallel, but we still got the consistent value of 76. So we have to be very careful when you call reduce, make sure what you're sending here is an identity value, not an initial value. So what you really want to do, if you want to really take the result and do some other totaling with it, then of course you have to do that over here and not over here. And as long as we understand these things, we can leverage parallel in those areas of code as well very effectively. So that's what we just did. We saw the effect of making the reduce parallel as well. Now let's talk a little bit about using the parallel stream. The question now is, how many threads can I create? So let's ask the question, how many threads can I create? Now, be very careful. This is like asking the question, how much can I eat? Not a good question. When I ask this question, I end up putting too much on my tummy. This is not healthy. So no, not a good question. And so the real question really is, what is the question I should really ask? And the question I should ask is, how much should I eat? Well, it's the same exact thing. How many threads should I create? There is a very big difference between those two questions. So it's not about how many can you. In fact, you can create as much as the memory will hold, like I can eat as much as my stomach will hold. Neither one of them is actually a good thing. So what is the answer to how many threads should I create? Well, it turns out there are some reasons why certain things are done in a certain way. But before we answer that question, let's talk about two different things that we should be concerned about. If I am doing a computation-intensive operations, if my operations are computation-intensive, what does that mean? I'm doing number crunching. You throw data at me, and I'm going to start using the CPU, and you can hear the CPU, the fans running. You can see the CPU really being pegged at the top. If you're running a CPU-intensive operation, then be careful. Number of threads that you create is less than or equal to, and this has to be less than or equal to, number of cores. This is something you have to be very, very, very careful about. If your job is competition intensive, you should never have more threads than the number of cores. Now, why is this so critical to follow? Well, imagine what's going to happen. Your tasks are computation intensive. They have a very high demand on the CPU. So the task is running on the CPU. What's the worst thing you can do now? You can go to this task and say, excuse me, could you please get off so I can get back on, do what you're doing? Which is kind of pointless, isn't it? This is like, here's a stupid example I'll talk about. Let's assume that there are 4 monks. And you know how polite monks always are. So there are 4 monks, but unfortunately, they go to a gym, and there are only 2 treadmills. So the treadmill T1 and a treadmill T2. So 2 monks get on the treadmill. And as soon as they get on the treadmill, they look around, notice there are 2 monks waiting for the treadmill. And being ever so polite, the monks say, oh my gosh, you are waiting. How rude of me to use the treadmill when you're waiting. And they get down. And the minute they get down, what happens? The other 2 monks get on the treadmill, and they look around and say, oh my gosh, you are waiting for the treadmill. How rude of you, and they get down. And they never work out. This is why it's good to be rude sometimes in life. So the point really is, just kidding. So the point really is that you don't want that to happen. You want to get on and say, you know what, it's my time. I'm going to just finish up this, and when I finish my workout, maybe you can get on, or maybe that's an opportunity for you to go find more treadmills to work out. Well, that's exactly the same idea. When you have a competition intensive, you never want to give more threads than the number of cores. What will happen if you do? Well, if you kind of imagine this graph in your mind, let's say this is going to be, the vertical is the time it's going to take. So vertical bar is time. Let's say the horizontal is going to be the number of cores on your machine. So I have a number of cores. Let's say you have a competition-intensive job on your hand. With 1 core on your, let's say you have number of threads is going to be equal to 1, let's say. Sorry, this is number of threads. Now, when you have 1 thread in your job, maybe your performance was that. So it took that much amount of time. Maybe now you give 2 threads, and you notice, hey, this is great. I got a little bit of a better performance. I got 3 threads. Maybe it's even doing a little bit better. This is giving you hope. Now, let's say you have on your machine 4 cores. Well, if you have 4 cores, you're going to hit that spot right there. That's going to be your performance. Now you have 5 number of threads. Remember the number of cores, let's say, cores equal to 4 on your system. But the number of threads now is 5, which is more than the number of cores. Now you will start seeing degradation in performance, and the more you go here, you might actually do even worse. In fact, you could even do worse than your sequential execution. I managed to do this on my client project, which was not fun at all. They gave me a piece of code that took 30 minutes to run. And I parallelized it, and it took 4 hours to run. And they lost all the faith in me when they looked at this. They said, thanks, Venkat. This was a really phenomenal improvement. We forgot to tell you, we want to make it faster, not slower. Oh, I forgot to see the requirements, sorry. Well, the point is, we're kind of playing with it. We got greedy, and we said, what if we increase the threads? And this is like the golden goose problem, right? You're trying to get more out of it, and you end up actually totally killing it. So you have to be very careful. Again, take this graph with a grain of salt, but the point is you're going to peak at the number of cores, and when you increase the number of threads to more than the number of cores, you're going to lose it. And as a result, you don't want to put more on it. We'll look at an example of this a little bit later. Well, okay, so we don't want to keep increasing this. So that's about competition-intensive operations. But what if my computations are I/O-intensive operations? If my operations are I/O-intensive, what does that mean? Well, I got some work to do on my CPU, but I'm going to do some I/O. I may read a file. I may write to a log file. I may read from a database. I may write to a database. I may send a request to a remote server. Whatever that I do, I don't have a use for the CPU. Let's say you were 0 less than blocking factor. What in the world is a blocking factor? The amount of ratio of time that you're not going to use the CPU. Well, if I'm not using the CPU 0 amount of time, I'm CPU intensive. That's why I'm saying this is greater than 0. At 0, I'm CPU intensive. And it is less than 1, because at 1, I have deadlocked. I have no hope of ever progressing. So I don't want to be 0 because I'm computation intensive. I don't want to be 1 because I am deadlocked. But if my value is between 0 and 1, what does that mean? If my value is between 0 and 1, then I have a little bit more to do here. I can now say the number of threads is less than or equal to 1 minus the blocking factor. Now, what this formula tells us is if you are if you are CPU intensive, your value of blocking factor is 0. 1 minus 0 is 1. So number of cores divided by 1 is number of cores. Make sure number of threads is never greater than the number of cores. On the other hand, if your blocking factor is 0.5, that means you're sleeping half the time. When you're sleeping, somebody else could use the CPU. So it's number of cores divided by 1 minus 0.5, which is number of cores divided by 0.5, which is twice the number of cores. So you can give me 2 times the number of cores if my blocking factor is 0.5. On the other hand, if my blocking factor is 0.9, you can potentially give me 10 times the number of cores. So the more I/O intensive I am, you can give me more threads, assuming I have enough work to do that is. If I'm CPU intensive, you drastically come down to the number of cores, never give me more than the number of cores I have on my system. So this becomes very critical to do. Now we can see why Java is doing things in the way it's actually doing. So we can talk about these things. So the question is, how many threads am I really getting? Before we can answer that question, let's ask the question, where are these things actually running? So to answer that question, we'll just keep the transform method right here and get rid of the remainder of the things. And now that I have my transform is here, I'm going to print on my transform the thread in which this thread is going to run. On the other hand, we're going to go ahead and call the map method over here. So we'll just go ahead and say on the collection we have, numbers, we're going to say over here, let's say numbers.stream. And in this case, let's go ahead and say .map sample, let's say, on this one transform. And then, of course, we'll go ahead and say .for each. We'll just swallow that little value that it provides for us. So given an element, don't bother anything to do with it. So this is going to display the thread in which the execution is running. And obviously, in this case, the thread in which it's going to run is going to be the main thread that we are really interested in using at this particular point. Well, we got a little 2-second delay. After that, it's going to display that value. Well, that's great. But in this case, of course, if I were to relegate this to a concurrent parallel threads, what is it going to do? Well, that's going to run in a parallel stream rather than running it on a sequential stream after all. So to show that it's running on a parallel stream, we can turn on the parallel. And what we're going to see at that point is, if I say .parallel right here, that's going to run on that parallel stream. But what thread is it going to run on is the question. If I go back and run this code this time, you can see that it ran on the fork join pool, but common pool. Well, okay, then let's take a look at that real quick. Before we do, let's get rid of these things just for a minute. We'll come back to these. Let's go ahead and ask the question output. Let's say runtime over here, and then .get runtime, and then we'll ask for available processors. So we can find out how many cores are available on my machine by asking for available processors. So this is going to tell us how many cores are on my system. So let's go ahead and run this one. And it tells us 8, which is a lie, by the way. But it tells us that that's how many cores I have. It's using hyperthreading and gives me twice the amount. I wish my salary was hyperthreaded too. But anyway, that's basically what it's giving us, that it's just giving us that twice that amount. So right there is my output available processors. Well, it says we have 8. Let's now ask the question, fork join pool over here, and then I'm going to say pool is equal to fork join pool dot. In this case, I'm going to say common pool and get access to the common pool. So let's go ahead and bring in the java.util.concurrent right there so we can ask for the common pool information. Once I get the common pool, the next thing I want to do here is simply output the pool so we can take a look at what it tells us. Now remember, it says I have 8 cores on my machine, but when I run this code here, it tells me my parallelism right here is 7. So my fork join pool, common pool rather, contains 1 minus, or number of cores minus 1. So it just has 1 shy of it. Why is that? The reason for it becomes really evident when we go back and take a look at this solution one more time. Let's go back to this code one more time and take a look at this particular execution. So when I go back and run this little code, you will see that it displays all these details. But did you notice while the transform is running in the common pool, our main thread is such a wonderful civilized thread. It says, gosh, I have nothing to do. Let me be part of this little fun you're having here. So as a result, the main doesn't sit there and twiddle its thumbs. While the main is blocked, the main goes off and does some work. This, of course, we know as work stealing. So work stealing is very essential to make sure we have better utilization of threads, and our main is going through work stealing right there, while the main is being blocked as a result. If you notice, it is going to be blocked here, let's say done. Well, the done is going to be printed by the main thread, obviously. So if I say plus thread.current thread, that's obviously going to be in the main thread. And of course, the for each has to print the result before it can come out of it. But on the other hand, if I go back and run this little code, you can see that it has not printed done yet. And when it is done with the whole thing, it says done from the main thread. But in the meantime, the main thread was participating in the job right there. So now you know why the common pool has 1 less thread than the number of cores, because main is actually part of it. Main is sitting there and saying, hey, the common pool, you're 7, I'm 1, will work together. In fact, you can see how careful they were in making sure they conform to that formula. It is less than or equal to. Had they created 8 threads in the common pool, and if the main had still participated in that, that would be a violation of that formula. You don't want to exceed ever when the computations are computation intensive. But the point is, they don't know what your computations are. So the safe bet is to limit this to number of cores. If your computations are, if your work tasks are not computation intensive, if they're IO intensive, you can create more threads, but they shouldn't do it for you by default. So they're really being careful at that point. So we saw how many threads are in there. We saw the formula for it. We saw the default number of threads available for us as well. But how do you then change the number of threads that you are going to have? One way to change the number of threads is to use this setting at the JVM level. But before we do this, let's take a look at one other thing. Notice that I have values in here. Rather than the 10 values, let's go ahead and say we're going to have 20 values to work with. So in this case, I'm going to simply say this is, let's say, 11, 12. Just for the purpose, we'll say these values I want to work with right here. So given these values, what am I going to do at this point? Well, if I'm going to run this in parallel and display this result, let's see what it's going to display. I'm going to remove this to produce a little bit of a less noise. So let's go ahead and remove that part for a minute. So we'll just stop it with this, and it's going to print the number. When I go back and run this code, you can see it prints the numbers right there, and then again. Well, what are we seeing? Well, remember, it says my machine has 8 cores after all. If I have 8 cores, well, then what happens is I have 20 values. Well, because the computations are almost taking the same amount of time, it is going to do by 20 over, in this case, 8 after all. So that is going to be about 3 batches of computation. So you're going to see 3 batches of computation, 8, and then the remaining 8, and whatever is left over there is going to come into the 3rd batch. So when you run this, notice, here is the first batch, 1, and then the 2, and then the third one right there, and then it's done. So that is in 3 batches it executed that, as you can see. So the 3 batches mainly because based on the number of threads we have, and it says, I'm going to do that first batch. When it's done, I'll do the second one. And then when the third one is over, I'm done, and it produced the result. Oh, great. On the other hand, what if I increase the number of threads for this? Well, I can increase the number of threads by using this entry called java.util.concurrent.forejoinpool.common.parallelism. I just love this flag because finally something longer than my name. So you can see that you can just configure this and change it. But I don't want to type this, obviously. I would get carpal tunnel syndrome typing that one. So I put this into a little script so we can run it and see. So I'm going to have a run config, and that's all I did. I'm just running the Java program, but I have provided that flag with a variable I can send the value to. So that's all run config is doing, just taking the value and sending it to that particular flag. But I'm going to ask it to run with 50 threads. And when I run this, you can see in this case, burst 1, and that's done. So all that ran in burst 1. So I put them all into one thread and said, run right now. But of course, in this case, we are giving it more thread. Well, the good news and bad news. The good news is you have this flag. The bad news is this is a terrible flag to use. Because if you use this flag, you are changing your entire JVM level common pool, and this can be a disaster in the making. Because how do we know what kind of computations we're going to perform throughout our application? There could be some things that are computation intensive, some things that are IO intensive, but if we're going to go back into the common pool, we're going to really make the performance really worse. So the general model of the story is learn about this flag and avoid it. And it's better to not use this flag because unless you're doing something very, very specific and like, I know this is exactly where this makes sense to use, kudos, use it. But the chances of that happening is extremely slim, so we have to be very careful adopting to this in general. So don't just get too excited about it. Well, you can also configure the flags programmatically in your application as well. But before we do that, let's understand how these things actually work. Now, let's go back to this code for a second. Notice in this example, where is the terminal operation happening? The terminal operation is the for each, and the terminal operation is happening in the main thread. Well, that's where I'm calling this. So I'm calling the for each in the main thread. But remember what main is part of. Main technically is part of the fork join common pool. So when you call this in main, main says, oh, you want to run this in parallel, I'm going to run it in my pool. Well, what is my pool for the main? My pool for the main is the common pool, and as a result, it's running in the common pool. But if the terminal operation is being executed in some other thread, which is in some other pool, then it would use that pool. So to understand this, let's take a look at a little example here. So I'm going to go back to this code. I'm going to go ahead and create this all the way up to here, but I'm not going to call the terminal operation. Instead, what I'll do here is I'll bring in stream, and I'll save this into a variable right here. So stream of integer, we'll call it stream is equal to, and we'll just save this into that stream variable. That's all I did. Now that I've saved into a variable, let's go ahead and call a method called process and pass the stream over to the process method. Let's go to the process method now. So public static void, let's say process. This takes a stream, let's say, of integer, and in this case, I'm going to say stream, and all I'm going to do is simply say stream.forEach, and in this case, we'll just swallow the result that is given to us, and we'll just do it this way. So again, no big deal. We're just doing still in the main, but it's a parallel stream that we are using. So when I go back and execute this code now, you can see that it's all going to run in the fork join common pool. In fact, we'll take a look at that right here to make sure that it's actually in the common pool. So go back and execute this little code and see where that's going to run. So when I go back and run this little code, you can see that it's all in the common pool that it's running. Great. Well, now that we saw that result, now let's get back to this code and say, well, I'm going to create a fork join. So in this case, pool. And this fork join pool that I'm going to create, let me make sure that I have concurrent up here. Yeah, I do. So, and I'll say pool is equal to new fork join pool, let's say of about 50 threads. And one of the things I normally like to do is to immediately say shut down, and then that way I don't forget it. Then I'm going to say pool dot await, let's say shut down. And in this case, I'm going to provide for asking it to wait for, how much time should I ask it to wait? Let's say give it about 10, let's say 20, 30 seconds. So this is going to be time unit dot, let's say, seconds. So I'm going to ask it to wait for a little while. Now, while it's doing this, this is going to be just waiting on the pool and giving us the result. After all, wait for that time to shut down. And this, of course, requires us to await shutdown. Let's see, await termination, right? Not shutdown. So await termination, that's going to require us to handle the exception. We'll simply say throws exception and not deal with it. And then, of course, the beauty of this is we get to enjoy this privilege all the way through up the chain. So now that we have that, we can simply say, what do I want to do within this call? Well, what I want to do in this call is I'm going to say pool over here dot submit. And within the submit, I'm going to take the stream given to me and say for each. And I'm going to ask it to take the element given and, of course, simply ignore it. So this is going to run the for each, the terminal operation, but within that pool we just created. No longer the common pool after all. Now when I go back and run this little code, we can, well, let's see what happened here. Unchecked, this is even better. So more exceptions to handle, this is awesome. So in this case, of course, what I'm going to do is run this within that particular pool where I want to run this, and this is going to be that particular stream, the lowercase s, that's what I was complaining about. So I'm going to run this within here, and as a result, you can see those are from the fork join pool rather than the common pool, the one worker. So we can see that in this case, it's all that little threads we create in our code rather than in the pool, rather than the common pool itself. So we can ask it to run in a completely different pool by simply creating our own pool and making sure the terminal operation runs within that particular pool. And as you saw here, it is not where you created the stream that really mattered. What mattered was where you ran the terminal operation for that particular stream. That makes a big difference. So that's basically what we saw in this little example. Well, that brings up the question. We can create our own pool and have that run within that pool. But unfortunately, we have to be, again, a little bit careful with these things. We can configure this programmatically. So what that means is you can maybe have different collections of pools around, and depending on the nature of work you're doing, you can decide which pool to dedicate that to. Maybe you have computation-intensive things in one pool, IO-intensive in another pool, and you can give it. But life is not that kind often, because your computation-intensive jobs may do some computations, and then what if they branch off to do IO-intensive after that? That makes it really difficult to manage as well. So in general, these are really good solutions when your problem is within a confine of things you can manage. But if your problem becomes totally convoluted and generalized and complex, we got to be extremely careful dealing with these things. This is just not something that's going to manage everything for you. That's one of the reasons why it's a master switch. They gave us these little tools, made it very easy to use the tool, but the decision to use these tools is a lot more difficult than using the tools itself. That's why we have to be very careful about it. Now, the next thing I want to mention here is parallel does not mean it is fast all the time. So how does it really matter whether it should be parallel or not? Well, before we talk about that, let's go back and revisit this problem we talked about. I got a little code here called computation.txt. Let's go ahead and use this little sample code here and see what this is doing. So all I'm doing is the compute method is going crazy over this two loops, one outer loop and one inner loop, and performing a little math. It's IO, it's computation intensive. Then, of course, I have a little instream.range, which is calling the compute method and performing a sum operation. My question is, how long does this code take to run sequentially? That is. So I'm going to go ahead and say, in this case, run.sh but I'm going to ask it to perform a time operation to see how much time that code actually takes to run. Well, in this case, it's performing the calculation. Hopefully, it produces some result which we can verify when we make it parallel also. And then when it finishes running, it's going to tell us not only the output it produces, but the time it took to run as well. Well, but it's a computation intensive. How many threads can I give for running this? As you can see in this case, the result was 2.2 E12, and then it took about 17 seconds to execute. Okay, fair enough. 17 seconds, I want to make this really fast. So what am I going to do to make this faster? Well, I'm just going to come and turn parallel right here as a very first step and see if it runs through and makes things really faster. So if I go back and run the code this time, because I said parallel, it's going to use the fork join common pool. And notice it produced the same result again. That's a good news, 2.2 E12. But this time, instead of 17 seconds, it took about 4 seconds. Hey, that's not bad. We got a good performance, better performance at least, by simply turning on parallel. But then we can say, aha, but you're only using the puny 8 little cores of yours. Why can't we just increase the number of threads even further? So to do this, what I'm going to do here is I'm going to create a fork join pool right here. So I'm going to say fork join pool. And in this case, we'll say pool is equal to new pool, fork join pool. How about 1,000 threads? And then, of course, I can say pool.submit. And in this case, we'll just go ahead and call that little operation. And we will just dump this whole thing inside of that operation for it to run and produce the result for us in the very end. And then, of course, I've started this on the pool. We'll say pool.shutdown. And then finally, we'll say, await termination. Let's give it about, let's say, it took about sequentially 17 seconds. Let's give it 30 seconds. Time unit dot seconds. And we'll ask it to wait that long and see what it's going to do. So in this case, we are putting it into a fork join pool. Let's just say 8 threads just for a minute. So this is really replicating the default behavior we're going to get out of this without much difference at all. So in the neighborhood of about 4 seconds, it should run. So sure enough, it took about 4 seconds to run. But I get greedy and I say, why don't I give you 1,000 threads? Well, it took 4 seconds, isn't it? So that should really run faster than that. And something tells us that, well, okay, so it took all that thread and gave us really no benefit at all. So it didn't really perform any faster. But what if I were to go back here and say, I'm going to give you 5,000 threads? This is where how much can I instead of how much should I? And at times that it doesn't really help us to run with more threads. Actually, that's, as you can see in this case, it's not really giving us much benefit at all, but in a lot of different cases, it could actually begin to perform really worse. If I were to go in and make some of these parallel as well, we could really hurt ourselves by doing it. So the moral of the story again is, don't go too far into these. It doesn't give you that kind of benefit when you do these things. But how many threads, what can I parallelize, what can I not parallelize? So to understand this, let's talk about a couple of different things. One is, when you are parallelizing, ask 2 questions. How many tasks do you have? What is the collection size? If a collection is really big, maybe it makes sense to parallelize. If a collection is really small, maybe it doesn't. You can do a little benchmarking and see whether it makes sense or not for the problem you have at hand. On the same note, if your task is really small, you might actually waste your performance by having threads. It might be faster to just execute it rather than create threads and execute it. If your tasks are time-consuming, you might benefit from having multiple threads. So a silly example I will use is, let's say you ran out of sugar and you yell out and say, hey kids, go to the neighbor and get me some sugar. You got 2 kids. One kid goes on, puts on helmet, and is going to take a bike to the neighbor, and the other kid jumps the fence. You know, who is going to get you the sugar really quickly? The one who jumps the fence. So if the distance is really short, you want to just go ahead and do the work. You don't want to go through doing, all these other ceremonies, which will potentially give you speed, but not in this case. On the other hand, if you want to go to a store, which is, let's say, 5 kilometers away, and get something, the kid that jumps the fence goes to the jail. You don't want that to happen. You really want to focus on distance and then map to the efficiency and then say how you can get that efficiency. That's one thing to keep in mind. So measure all the time and see if you're actually getting the performance that you would really like to get. On the other hand, there is something else we have to be very careful about as well. And so I'll switch gears and show you a slightly different example to understand this. I have a class called person.java. The class person has name, gender, and age. And in this example, as you can see, I have the age and the gender and the name and all these little details. But what I want to do is I want to say create a person, and I'm going to create a bunch of people on my hand. So in this case, you can see I have a Sarah who is female, and Bob who's male, and Paula who's female, different ages. And I'm going to take this Jill. We'll make Jill older for now. So Jill is 42. But I'm going to ask the question of this. I'm going to say in here, find the first, let's say, female. So find the name in uppercase of the first female older than, let's pick a number. Oh, let's say older than 30. Well, I'm asking for the first female who's older than 30. Well, in this case, what are we going to do? Because it's the first one, I'm going to say create people and then dot stream. Then I say dot filter. I'm going to say given a person, well, it's a female older than 30. So let's say person dot get gender is equal to gender dot female. And then I'm going to say dot filter, given a person dot get age, and we'll say is greater than 30. And then finally we'll say map, given a person, get the name of the person. I will say get name. And we want it in uppercase, we'll say string dot to uppercase. And finally, but we really wanted only the first person, so we'll say find first. And what if the person doesn't exist? We'll say or else nobody, so no one. Well, I want to print the result of this eventually, so we'll go ahead and print the result right here. So output, and we're going to ask it to display all these different values for us. If I run this code, you can see from the output it's Paula. Why is it Paula? Because Paula is the first female who's older than 30. And because it's first, it's an ordered collection. Because list is an ordered collection, the ordering is kept, and it's Paula. It doesn't matter how many times I run this. No matter how many times I run, it'll always be Paula. But one thing important to keep in mind is streams not only have elegance, streams also have efficiency based on laziness. So what does that really mean in this context? If I go back to the code, if I display the get name and get age and get gender, I'm going to display these values in these particular output. So you can say get gender right here, and as a result we can say get gender for name, and we can display the gender details or return the gender details. But because of laziness in the computation, what's going to happen is, remember, it does not take these functions. This is one clear distinction in how collection streams work in Java 8. A stream, it does not execute a function on a collection of data. It instead executes a collection of functions on a piece of data. So this is a very clear distinction of how streams work in Java 8. So it doesn't take the collection of data, all the people, and run a function. That is a function. It doesn't do that. It doesn't say, oh, thank you, you gave me a function, I'll execute on the collection. Oh, no. It instead takes a collection of functions. It takes those highlighted functions as a collection of functions and fuses it. And then it says, I'm going to run that collection of function on the data. This is a very clear distinction as to how streams work in Java compared to a lot of different languages that may pretend to provide functional style of programming, but don't give you this efficiency. So this is one key thing, which is the way laziness is baked into Java. Lazy evaluation is possible because of that. Well, this is very keen because when you run this code, notice it evaluated Sarah, given this list that you see here. It evaluated Sarah's gender, age, and another Sarah's gender, age, then Bob's gender but not age, Paula's gender, age, and name, and the minute it found find first, it said, I'm done. And it bails out. It never touches Paul, Jack, or Jill. So Paul, Jack, or Jill were never bothered. That is efficiency. We are lazy evaluating. We're not doing any extra work than necessary. This is really good. You can also do, instead of a find first, you could do a find any. Find any means I don't care about the sequence. Just give me the name of any female in the collection who's older than 30. But because the execution is sequential, and because the collection is ordered, Paula gets the fair advantage. No matter how many times we run, it'll always be Paula. So going back to this example, let's remove this output for just a few minutes. If I go back and run this now as run.sh, it's going to be Paula, and it doesn't matter how many times I'm going to run this, it is going to be always Paula. I know this is not a proof to run it 20 million times and then monkey it around and prove it, but at least empirically we can say it's not giving us any different result. So that tells us it's Paula all the time. No matter how many times we run, it's going to be exactly that particular call, and we can kind of take comfort in that. Okay, great. On the other hand, if I go back to this code one more time, and this time I'm going to say find first one more time. Remember the for each ordered. For each ordered gives you ordering, for each doesn't. Well, find first always imposes ordering. You don't have a find first ordered. Well, the first itself is ordering, right? So you don't have to say find first order, it's find first, it's ordering imposed. So in this example, if I go back to this and say parallel right here, now we are saying go run this in parallel, but give me the first person who is older than 30 and who is female. If I run this code, it doesn't matter how many times I run, it better be Paula all the time because it is ordered. The collection is ordered. Find first will preserve the ordering. That's going to be Paula all the time. However, if I say find any, all bets are off now. Because the collection is ordered, sure, but it's find any. So because we are running it in parallel, there is no particular sequencing of execution. The one that it hits first, it's going to come back with the result. So in this case, look at the answer that's possible now. There are only two people who are older than 30 and female here. That's Paula and Jill. So sometimes it could be Paula, sometimes it could be Jill. Who knows what it would be? So when we run this, we can see that was Jill. Okay, this is unfair. But okay, thank you. I was kind of beginning to doubt myself. So you can see that it could be any of them. Sometimes Paula, sometimes Jill, and you can go back and forth. There's no guarantees to it. Well, this is all reasonable, isn't it? That seems like that's the way it should be. However, we have to be very careful about one thing though. What about laziness and at the same time also parallel? Well, let's understand what this really means. Notice if I run this sequentially, remember we never touch anybody other than after Paula. We will not touch Paul, Jack, and Jill in this example, and that is because we are doing it as sequential and we are doing it find first. And as a result, when I run this, we never touch Paul, Jack, or Jill. On the other hand, the minute we turn parallel on, what does this say? It says, hey folks, let's get the party started. And as a result, it unleashes the thread on the collection. And as a result, notice what's going to happen. Your result is always going to be Paula in this example because you said find first. We proved that earlier. However, when I run the code with the output showing, you will notice we are actually touching Jill, we are touching Paul, we are touching Jax as well. And as you can see, this is unleashing on it. So what does this really mean in this context? So to understand this, let's take a slightly different example. We got a number of people in this room, and let's say I was sitting over there, actually I was, and maybe I left my smartphone next to the third gentleman over there. Now there are two ways I can solve this. I'm like, I don't remember where I left my phone, so I could go over there to the first gentleman and say, is my phone next to you? He says, no. Is the phone next to you? He says, no. Is the phone next to you? He says, yes. Oh, great, thanks. I took 3 units of work. How many people did I bother? 3 people. So 3 units of work and 3 units of time later, I got my phone. Alternately, what I could do is I could just yell out in this room and say, folks, looks like I left my smartphone somewhere. Could you please check to see if it's there? And everyone, hopefully, will start looking around for my phone. And what's going to happen now? Good news, I'll get the phone in 1 unit of time. Well, let's revisit this. What is the difference between these two? Hey, isn't that good that I'm getting the result faster? Let's try this again. I'm going to yell out and say, get me my phone, please, if it's next to you. So the good news, I got the result in 1 unit of time. Bad news, I bothered everyone in the room. Good news, I don't care. So that is exactly what this means. Parallel says, I don't mind wasting more resources with the hope of getting the results faster. So if I'm going to get the result faster, I will unleash my threads on it. I may even do more work while some work are still being done. If other work finishes and I get the result faster, I am happy for that. So that is exactly what this says. Parallel is, laziness says, be efficient. Laziness says, don't waste your computations. Don't do any extra work. Just be efficient. Minimize the work you do. That is what laziness says. Parallel says, unleash your threads. Do as much as work as you can, you need to do with the hope of getting the result faster. So you're not keen on resource utilization at this point. You're keen on speed of delivering the result, and we need to be very careful. If you have an infinite stream, that is, and if you're opening an infinite stream with parallel, think about it a lot. Because your streams are going to start kicking very quickly, and all those you will get the result faster, but your performance is going to go down because all those threads which are busy are going to be still kept busy because they don't have a clue to die. New threads may not be created after the task is done, but all the threads you unleashed might potentially be doing some work, and that may not be a really good thing to do. So that's where I'm going to stop talking about parallel, and we're going to talk about completable future. It's probably a good idea to give you a little break. How about a 10 minutes break? And at the end of the 10 minutes, we'll come back and get started right back here. Thank you. All right. Let's get started again. Thanks for returning back. We will talk a little bit about completable futures and look at some of the nice things that we have available here. So we looked at parallel streams, and I mentioned that it's really useful when we have a collection of data, a parallel array problem. We want to take this collection of data and do things in parallel. That serves really well when it comes to parallel streams. On the other hand, what if we have a task and we want to just divide and conquer that task? We want to take a task and maybe just delegate that and ask it to run asynchronously and come back and give us the result. Well, in this case, an asynchronous execution can be very useful. In Java, traditionally, we have done almost everything using threads. Oops, thank you. Thanks for alerting me on that. Not sure why that went that way. Let's, So that's messed up too, isn't it? Yeah. So let me try to see if this one helps. No. So it looks like a resolution is messed up on the other side. Can you check on that, please? Thank you. Concurrent problem, I think. So, so while we're looking at it, we'll just continue to talk and signal me if you see that getting fixed. So one of the things we can do we kind of approach almost everything in Java using multiple threads. Well, when it comes to multi-threading, let's say you want to send off a task to execute, but you want to get the results back from it. So what do we do in terms of how we can get the results back? So no, that doesn't seem to fix. Let's see if I can change the resolution here. Oh, cool. All right, thank you. I didn't do anything. That's the worst thing. So, all right, thanks. So anyways, so let's talk about, you want to do some task and get the result back from this. So how do you really do that in Java? Well, let's think about this for 1 second because this is a bit scary. When you start with the threading all the way back, remember what the function was? The runnables run method. What was the run method of runnable? Void run that. Just think about that for a minute. It says, I will not take any input and I will not give you any output. How rude. This scares me, right? Because the fundamental API behind multi-threading said, I won't take anything, I won't give you anything. What does that mean? The only way you can do anything with this is by doing mutation. But didn't we say mutability is really bad idea when it comes to concurrency? This was dead on arrival. I mean, I use this as an example to scare my children normally, right? You'd say, this is how life is when you get out there in the real world, right? You got to face these things. So we said, okay, we really want to do some work and we want to get the result back. How do you really do that? Well, this is where we could use a future. Well, at the beginning, future sounded like really a good idea. But you call a method, what does it do? It gives you a future. What do? You call get on the future. And the minute you call get, what happens? You get blocked. That's no future at all. It's a very bleak future. Well, I know this is really a scary thing to say, that we can actually learn something from JavaScript, but it truly is. Because the JavaScript programmers have really felt these pain for a long time. Remember, JavaScript fundamentally is an asynchronous programming language or environment. And so they have been through this in the past. They used to do callbacks. Well, when you do callbacks, it is very, very painful. Well, the first problem is callbacks lack consistency. When you use a callback, is the first argument an error or is the first argument data? Who knows? It can be anything you want it to be. And it's very hard to compose it. You have a callback which returns a method which has a callback, which returns a callback. I want a callback. They have a favorite name for it. They call it callback hell. And that doesn't go really well. And of course, it's very hard to deal with errors also. So what the JavaScript world did is they came up with what are called promises. I really think that promises opened up some good possibilities. So what do promises do? Well, a promise may be in a 3 different states. It may be a resolved, rejected, or pending. Well, a promise may have one data going through it. And how does a promise really work? Well, this is the nice thing about a promise. A promise has 2 channels. So when you look at a promise has what is called a data channel, and it also has what is called an error channel. So think of this as 2 tracks, a left track and a right track. And when you have a promise at the head of this, so right about here, let's say we have a promise, and from the promise you may have a data that gets generated, and that may propagate through the data channel. Or you may have an error that gets generated, and that may propagate through an error channel. So in other words, a promise gives you 2 tracks, and the data may go through the data channel from the left to right, or it may go from the error channel from left to right, which is really nice because you're able to deal with data and error through this very nicely. But what is really cool about this is beautiful to compose. How do you compose it? You can take a function that returns a promise, we'll call it func, and then on this you can say, and you can put a little function, you can put a little catch over here and put a function. Now notice, that's your data channel, that's your error channel. Then you can say .then, and you can put another function, we'll call it f2, and you can put another catch over here, we'll call it e2. And let's call this one as f1, and this is as e1. The way this is actually structured is, this will be your f1 followed by f2, and this will be your e1 over here, followed by e2. So this is a composition of this function. They form a nice chain of functions. So when you generate a data in the function, if it was a real good data, it'll go to function f1. If that produces a nice data, it'll hop on to function f2. If that produces a nice data, it'll hop on to f3, and so on, and it would just keep going this way. On the other hand, if something were to go wrong in the function, you would then come to e1, which will do something and generate an error, which will hop on to E2, which will generate an error, and then it'll hop on to E3, and then so on, and it can continue. But what's really cool about this is, you may have a data you're processing, and let's say right here when you're processing F2, something goes wrong. So the original was good, F1 had no problem, F2 chokes up and says, I don't like this, it tastes really weird. Well, now it can put you on the left track and say, go to the error. Now you're starting to process the error. Maybe this E7 says, you know what, I can handle this. I can make things right. At this point, it could potentially put you back on the data track again. So you can go from the data track to the error track to the data track, and back and forth. So promises give you a nice way to compose these functions. I know you're wondering, that's all awesome, but why are you talking about promises and JavaScript? Wouldn't it be so cool if Java has promises? Well, that is the most remarkable part. Java has promises. But in our field, we'll never give the same name somebody uses, because then people will understand it. So you kind of give a completely misguided name, so nobody has a clue what you're talking about. So what is it we are really talking about? So in a sense, Java's completable futures are JavaScript promises. So this is exactly what we have with us today, and we can benefit from it really nicely. So Java's completable futures really are JavaScript promises. And everything I described to you just in the past several minutes is actually for completable future. That's exactly how completable future works. You can go back and forth in this chain, and you can use it. We're going to see how that works in just a few minutes. So what are we going to see here? We want to create a completable future and work with it. Well, these are the stages I talked about. So you can have stages of these functions you can go through, and you can work with them. So when one stage completes, the next stage can kick in and do the work. And so that becomes a nice way to compose these chain of operations. Let's look at an example of creating a completable future. There are several options available for this. So we'll look at some of these options. Concurrent, and then this is going to be concurrent.completable future. So we'll say completable future right here. And in this case, of course, we're going to create an example and play with this little thing. So we'll go ahead and say completable future dot. Let's start with a little action to begin with. So I'm going to say run async right here. And within this run async, I'm going to just give it a little runnable for it to work with. I'm going to say over here, let's call this as, let's call it as do work. So do work is my async, run async. I'm going to say, in this case, in main right here. And we are running this as a completable future. So the minute I say run async, that goes off and does some work, as you can see, while the main thread is doing its work. So that's as simple as how we can create a little asynchronous operation to run. Of course, you could have done, thread and then runnable, and then you could have said executor services. Well, this is almost the same as that, except that it's much easier to do this. Of course, the question is, where does this actually run this code? Well, we'll figure that out a little later. So we are just asking it to run some task and do the work. So that is doing that little work. But I want to do some work after this finishes the work. How do I actually do that? Well, that's the beauty of this, is we can say then over here and accept. And in this case, I can simply say next stage, if you will. So you can compose these operations very elegantly, and you can keep moving forward. It's complaining that there's an incompatible type in this case because the other guy is giving us a void. We'll come back and work through this, but look at the structure for just a minute. So you can start going through this pipeline of operations and do stages of operations, and we'll take a look at how we can do this in just a second when we look at a little bit of a broader example. So, but I want to get a result back from this computation. How do I do this? Well, I can go back to this completable future. Rather than doing a run async, let's go ahead and say, in this case, supply async. Well, as you can imagine, run async took runnable. Supply async takes a supplier. So the supplier functional interface is what we're going to use over here. So what I'm going to do in this case is, just to give you an example, I'm going to output do work, or doing work, let's say. And then when I'm done with the work, let's return just a value of, let's say a value of 2. So this is going to return a result of 2 when the work is done. So when I run this, you can see it says in main and doing work. but I want to get that result back from the call. How do I get it? Well, if I want to get the result from the call, I can go to this completable future, and let's just take this little code right here to make it a little bit more elegant. We'll go ahead and say this is going to be sample generate, so that way it's easier to see this, and we will put this as public static, let's say int generate, and this is going to not take any input, but it's going to do that little work. It's going to say, doing work right here, and then it's going to return that value of 2 when the whole thing is done. So in this example, as you can see, we are able to get the result back from the caller. Well, that is going to be the generate function doing the actual work. But then I can say .get, and then in this case, I can receive the data, and I can try to print this out. So what is it going to do? Well, that's the completable future. I set it off to run separately, and then I'm asking it to get the result. Of course, when we do this, it wants us to handle the exception. I'm going to just throw that up here and say throws exception and be done with it. So in this case, you can see in main, but we printed the 2, but the 2 got printed when we got the result back from the call. But unfortunately, the problem with this approach is we're going to block and wait for this to finish. So generally, get is not a good idea because that was the problem with future as well. We call get and we get stuck with it. You could put a timeout on this, of course, but that's no fun either. Well, one other option you have in this case is, let's say this is going to take a little longer to run. So I'm going to say sleep over here dot sleep, let's say. And in this case, if I'm going to ask it to sleep for a certain duration of time, let's say 2 seconds. Well, it's going to sleep for 2 seconds. What's going to happen when I run this? When I go ahead and run this little example, you will notice it's blocked for that. And then when it is done, it prints 2 and moves on. Well, that's unnecessarily waiting. What if I don't want to wait for that long? You could say get now with a -1, for example. In this case, if I don't have a sleep, well, let's go ahead and say I'm going to wait a little longer. This may not actually finish it, but we'll find out. So when I run this, well, it's still got a -1. That is what get now does. It's pretty impatient. I want it now. So if you want to put this into a variable and come back and call it, that might actually help. So in this case, let's grab this one and say completable future of integer, let's say, and we'll call it as future is equal to and save it away. And then in this case, I'm going to say, let's put a little delay in here too. So sleep of, let's say, sleep 1 second, or maybe in this case, 1 second. So it gives a little time for it to get up and finish the job. And in this case, of course, we will go ahead and say, I want to output here future.get now. Well, clearly, there's no sleep here. So by the second, this 1 second it comes here, this should be done. It will not be a -1, but a 2 is to be the result of this particular computation. And you can see it produced a 2. On the other hand, if I were to sleep a little longer than when it asks for the result, that'll be a result of -1. So it can be very impatient to say, get it now for me. Well, that is good. That is still not very appealing. So we can just quietly move away from those. We'll see how there are better ways to handle this. Let's talk about the thread of execution. What thread is going to execute all these different calls? Well, to understand that, let's leave this generate right here for now. Let's remove the sleep. Let's come back to this future that we created. And when we have this future saved away in the generate, what I want to do is I want to come in here and say the future dot then accept. And then accept, given a piece of data given to me, I want to output the data right here. So what does this really do? Well, it's going to go through a second delay and then come back and tell us that it's going to bring back the data and give us the result of it. Oh, let's say in this case, then accept, not the accept. So then accept. Well, what does then accept actually take as a parameter? The then accept takes as a parameter a consumer, which of course gets the data and displays it, does whatever it wants to do with it. So that is an example of how that is working. But I'm curious, where's all this running after all? This is one of the cool things we can really enjoy. So to understand this, I'll say sample printed, and let's go back and write a sample printed function so we can play with these threads and observe this. So I'm going to say over here void, we'll call it as printed, and in this case we will simply print out 2 things. We'll print out the value that we get, plus we'll also print out the thread.current thread. So we can see what thread is executing it. Likewise, doing work, and then we'll say plus, in this case, thread.current thread, so we can display the information about this thread. Well, when I run this code, what's going to happen? Well, let's step back and see this real quick. In this case, notice that we are calling the future. Well, the supply async is taking generate as an argument, and as a result, it is going to execute this in that other thread, which is good. On the other hand, what about this print it? What thread is it going to run in? That's the puzzle. We'll answer that puzzle in just a minute. Well, remember, in this scenario, if I don't have the sleep function right now in here, but imagine I'm going to put a little sleep method over here. So I'm going to say over here sleep, and I'm going to ask it to sleep for about a second. Let's understand the scenario. We started a thread right here. We asked it to print the result of that particular asynchronous call, and now the main is blocked sleeping. In the meantime, this guy kicks in, he does his work and says, now that I'm done with this, I might as well join in and finish this job. So when I report the thread of execution in this example, what I notice is, it's a common pool thread 9 and 9. Well, that exactly did both the pieces of work. The common pool thread did this work, but it also did the print it while the main is waiting. On the other hand, let's put a little sleep right here. Now what's the scenario? This asynchronous task started up. Main is sleeping. Main has not told us what to do with the result of completable future. That's one of the really nice things is completable futures don't expect you to be really fast. You can be as fast or as slow as you want to. So if you're not ready to use the result, it doesn't force you to use the result. You can take your time. But it's not going to wait around for you in terms of execution. So it finished the work, put it in the completable future and said, here it is, use it when you want to. You take your sweet time, you come and call this. What thread is this going to run in? Well, the main says, I don't have anything to do right now. I might as well do the work. So when I run the code this time, though, notice that that was executed in the other thread, but the 2 was executed in the main thread and not in the other thread. And that is because by the time main calls the println, that execution is completed, the main might as well do the work. That is fairly efficient, isn't it? So when you look at a completable future, your particular call may be asynchronous, or it may be synchronous. You cannot quite say that based on what you're looking at. It is going to be efficient. If it's going to take a little longer, it's going to run in another thread. If it's not going to take any time at all, it can run right there, so it can go either way. So that is basically the thread of execution. But I want to run this in a different pool. I don't want to run this in the common pool. What do I do? Well, there are a couple of things we have to be very careful about. The first thing is, when you create the supply async, what you can do here is you can provide a pool right here. I'm going to call it as pool 1. So I can specify a pool when I create this. So in this case, I'm going to say a fork join pool. We'll call it as pool 1 is equal to new fork join pool. And I've created this pool called pool 1, and I've scheduled it in pool number 1. So I can give the pool after setting the task to run. Then I sleep for a second and ask it to print the result. Well, in this case, when I go back and run this little code, let's see what it's going to do. Notice that's from not the common pool anymore, but from the pool that we created. That's still running in the main. So that's pretty awesome. Same token as before. If I don't have a sleep here, then by the time I get through this, the computation may not have been finished. So where is this println going to run now? As you can see here, both of those lines are running in the other thread, not in the main. So that works really well. So putting it into another pool was extremely easy. However, you say, all right, that's all great so far, but let's focus our eyes on this one. I know that this can be running in that other thread, or it could be running in the caller's thread itself. But what if I want to give a completely different thread for that stage of execution? Remember when we did parallel stream, we quite didn't have the power to vary the parallel versus sequential. The entire pipeline was condemned to run in one pipeline, one thread. Well, that's not the case with completable futures. You can take the stages of completable futures and you can put them in different threads. How do I do that? Well, that's where async versus non-async comes in. If you look at this example here, where is this running? Obviously, that's running in this example in that other thread. So notice it's pool 1 that it's running in. But instead what I'm going to do here is I'm going to go to this guy and say, then accept async and provide a pool 1 again. We'll start with that first. So I'm saying run it in pool 1, please, not in the main, which is what it was actually doing, isn't it? So that's what it's doing. But on the other hand, if I put the sleep over here, what did we notice earlier? This one was running in the main earlier, if you remember. Now when I go back and run this time, notice that this is running in the pool also, not in the main, because you specifically told them, don't run in your own thread, run in the other thread. Where this becomes really cool is, this could be pool 2 and not pool 1. So in this case, I could create another pool, and I can say this is, let's say, pool of 10 threads also, or 15 threads, 5 threads, and this is going to be pool 2. And why would you want to do this? Well, maybe these tasks are computation intensive, maybe these tasks are I/O intensive, remember? So you can start varying the threading model that you want to provide, and so you can control that maybe a little bit better, or for whatever other reasons you want to do. So this is pool 1, as you can see, whereas that one is pool 2. So you can control. So what's the model of the story? Almost every function has an async version, which allows you better control on the threads of execution of those functions as well. So it's quite a complex number of options available to you in terms of how it gets handled. Now that we saw that, let's understand a few beautiful things we can do with this. So in this example, just to keep things really simple, let's go back to the generate function. The generate function generated a value of 2, as you can see. Well, that's great. I have a value of 2. I'm going to remove these outputs for a minute. I'll just output the value given to me so we can actually just look at what's going on in this example. The value being generated is 2. So what am I going to do here? I created a future, as you can see right here. And in this case, the future I created is simply getting the generate function. Well, then I can take this call to the generate, the supply async. I can beautifully draw a pipeline. So now I can say dot, and I can say then accept, and then I can say given a data, I want to just print the data. So I can say print it and send the data for printing. So if I execute this little code, notice it printed 2. Well, the generate produced 2, then accept printed it. That's a nice pipeline. So this is kind of like your for each, isn't it? So then accept is kind of like your for each. So let's put it as then accept is like for each. So leave it at that for a second. Okay, so we brought a similarity between this pipeline of CompletableFuture and pipeline of streams at this point. That is then accept. But what if I don't want to accept and print the data? Well, I could also do a then run. Then run will not take any data. We'll just do it action without any data. But I can also do, this is really nice, a then apply. Well, you kind of know what then apply is kind of, right? So then apply is like map. So it can perform a map operation for you. So in this case, what I'm going to do is I'm going to say dot then apply. And in this case, I'll say given a piece of data, give me data times 2. Well, remember, generate gave us a 2 on line number 8. This is going to take the 2, double the 2, that becomes a 4 when it's returned, and this is going to print out the value of 4 when it's done. So right there is the value of 4. So this is like a map operation. It performs a transformation. Now you could say, why didn't they call it as a map? Remember, you never give the name others will understand. So as a result, they said, we'll call it then apply. It's a lot more fun. It could have been called as map as much, isn't it? Because we're just transforming it. That's what we are doing. But the for each wouldn't make any sense per se. Let's give that because for each, well, gosh, this is going to only have one value, not many values. So it's not a for each. It's a terminal operation. Okay, fair enough. So given that, what do we do? I mentioned what then run will do. It's a terminal operation. Just do an action and you're done with it. So you could use that too. So we can create a nice pipeline, but notice that I created these things at the top, at the origin. What if I don't want to create this at the top? What if I want to send the data at a later time? You can do that very nicely as well. Let's see how we can do this here. So notice what I'm going to do now. I'm going to say CompletableFuture, and in this case, integer, and I'm going to call this as future is equal to new completable future and create a future object right there. Now that I created a completable future, I'm going to replace this with future dot. Well, notice this future has not completed yet. It doesn't have any production yet. So I can come to this future and ask the question, future dot is done. And it tells me at this point, no, I'm not done. I'm still pending. So this future is not done yet. It's still pending. Until it completes, you're going to wait for it. Similarly, you can ask it, are you canceled? Maybe somebody really canceled it. So I can ask it, are you canceled? And of course, at this point, it'll tell you that it's not canceled either. Great. Now that it's not completed, not canceled, what can I do at this point? Well, now I can say, let's say sleep, let's say give it about, a 10 second, 5 second, 2 second delay. And then I'm going to say over here, future dot. And in this case, I'm going to ask it to complete it. So complete, let's give a 7 to it. Well, I can push the data through this pipeline of futures. And again, throwing a 7, but you could do other work and get the data. This could be somewhere else. You could pass your completable future to somebody else and say, you take it, and then you tell me when you're done. So this is a nice way to you build a pipeline. You give the head of the pipeline to somebody and say, you work on your thing. When you're done with it, send me the result back. This is like you want somebody to do some work for you. You say, you do the work. When you're done, text me the result. That's exactly what we're doing. You build a pipeline, give them the future and say, you go push it when you're ready, and they can call complete on you. So you don't have to attach the head. The head can come in at a later time. What is this going to do? 7 times 2 is 14, and the result should be printing the 14 after a 2-second delay, and right there we see 14 being printed. So this is a nice way for you to build the pipeline and then come back and execute the pipeline later on. At this point, I want to remind you the main difference between completable future and a stream in this case is a stream is a 0 or more stream of operation. Completable future, there's only one sequence through which it goes through. And the minute one sequence goes through, a completable future either completes or it terminated, it was canceled. You won't get multiple streams of data through a completable future. This is one of the biggest differences between promises and observables and streams. Promises are 0 or 1 piece of data or an exception. Observable is 0 or many pieces of data. It's a stream of data. So if all you're doing is just one stream, one piece that is going to transform through a completable future, our promise works really well. So we saw how to do that, but what about exception handling? Well, if things can go wrong, it will, and we need to be able to handle that. Well, remember what I mentioned earlier. Promises have 2 channels. They have data channel and they have the error channel. We have to be very careful how we handle this, and so let's understand this with a little example. So in this example, I'm going to go back to my generate method. So in the generate, I'm returning a 2, and notice in here, completable future dot, let's say, supply async, and then I'm going to specify sample generate, and I'm going to just put this pipeline through it. That's going to generate a result for us, absolutely. And as a result, what is it going to do? So when I run this little code, you can see that generate generated a value of 2, and that's going to propagate through right here and produce the result in the very end. Let's just do a sleep here. Well, actually, let's go ahead and output this and see what it produces on the output. So when I run this, you can see it printed a 4. Well, that's printed 4 because generate created a 2, transformed 2 to 4, and printed it. But what if something were to go wrong here? So I come in here and say, in this example, let's say throw new runtime exception. And we'll put a very useful message. Oops, something went wrong, right? So just like we get error messages, right? Very useful messages. So something went wrong. So this is going to blow up. What's going to happen when it blows up? Just for our purpose, let's go ahead and run this code and see what it's going to do. When I run this code, notice we didn't get anything. That's kind of silly. Why? Because we never really did anything on our error channel. The data channel has been laid out. We only bothered about the data channel. What did we say? The data produced is 2, map it to 2 times 2, and print it. So we took the effort to build this data channel, this came to 2, and then times 2, and then print. That's the data channel. We totally forgot the error channel. Now, in this case, this guy is blowing up with the runtime error. Oh my gosh, what do I do with the error? Maybe I want to print the error. Maybe that's what I want to do. I want to print the error. Well, if I want to print the error, how do I really do that? Well, let's get back here, remove these for just a minute, and we will say then, and we can say in this case, exceptionally. I really, really hate this word. It doesn't feel good at all, right? It's not exceptional. It's like, gosh, we're dealing with a failure. So exceptionally, what are we going to do? Well, you're going to give me a throwable. And when you give me a throwable, what do I want to do with the throwable? I'm going to say output the throwable for me. So I'm just printing the throwable at this point. I remove the data channel now, only focusing on the error channel. We'll bring them back together a little bit later. So what is this going to do for us? Well, in this case, it complains in compatible type, bad return type in lambda, and it wants us to return an integer value. We'll just make it a little happy for now. We'll come back and fix it a little later on. So in this case, I have a throwable, and then I'm going to simply put a little curly, end this one, and then end this here. And for now, we'll clean this up a little bit later. And all I'm going to do here is, let's say, return a 0 for now. Don't worry about that value at this point. When I run this code, what does it really do? When I run this, notice it printed exception and the details of the exception. Let's make this a little bit more easier to work with. So I'm going to say public static. We'll say in this case int, and we'll say process error, and we will say throwable, in this case throwable. So throwable is th, and all I'm going to do is output throwable, and what am I going to do? Return 0. So at this point, a throwable returns 0. Just like this, I just moved it around. That's all I did. So we'll just make it a little bit more civil. So sample process error. And when I go back here and run the code, it should produce the same result as it did before. Well, almost. We'll just do one more thing. We'll just say error colon, and then just make it a little bit easier to see dot get message. There we go. So I'm going to print the message here and move on. So when I run this code, you see error, oops, something went wrong. Great. So that's the error channel. So what did we do just now? We took this error and we printed it. Well, okay, but how is all this coming together? We want to have an error channel. We want to have a data channel. Don't we want to live together and be happy? Well, careful though. Notice what I'm going to do now. I go here to this guy, and I take this exceptionally and I drop it here. And then I remove these two. Be very careful when you do this. This is how JavaScript promises work. This is how Java Completable Future work. Very careful. What you're saying here is, I'm going to take this one. If there was a failure here, I will step into exceptionally. If there was no failure, I'll bypass exceptionally and go here. Up to this point, I'm sure you're all happy, right? Gosh, that's the way it should work, Venkat. Yes. But the question is, when this fails, it goes into exceptionally. What does that function in exceptionally do? This says, I got this. I recovered from the error. My new result is 0. So the meaning of this call is, I am going to put you back on the data track at this point. So this is redirecting you back to the data track, right? And as a result, and because this is before the transform, you are actually going to come in here. This is the meaning of the code you are seeing right now. So as a result, what is going to be the behavior of this? This fails with an exception. This prints the exception, but generates a new data 0. 0 times 2 is 0, and I'm going to print the 0 in the very end. So when I go back and run this little code, you can see in this case, oh, illegal, there's a semicolon. Okay, that's exceptional. Okay, so let's go ahead and try this again. And in this case, of course, I'm going to go back and run this now. And what does that do? Well, notice runtime exception. Oops, something went wrong. Where did that 0 come from? That 0 came from the transformation of the data 0 from here, which was multiplied. If I say plus, you will notice it's a 2 instead of a 0 because it took the 0 and did this. So the question you should ask very clearly is, are you dealing with the exception and recovering from it? Or are you dealing with the exception with no hope of recovery? If there is no hope of recovery, don't return a value. What you want to do instead is throw and just rethrow it if you want to, or throw new runtime exception. I hate to tell you this. And so you can just propagate this further. And if something else comes in the chain later on, it can handle it. If there's nothing else in the chain, it just evaporates. So let's go ahead and run this and see what happens now. When I run this time, though, notice, oops, something went wrong. You don't get the result of 0 or 2 anymore. Why? Because when this failed, you're not going to do this. It is instead going to the next exceptionally. And what am I going to do in this exceptionally? I'm going to just take my easy route here. I'm going to call process error again and then send it back to this. So what's going to happen then? That's going to, of course, tell us error, I hate to tell you this, and it blows up again. So that's what we are supposed to see, right? Let's see if that works. So go back and run this again and see what it tells us. Oh, bad return type again. Well, that's because I put this after this because it's what do you say? It's a consumer, isn't it? So we'll put it right after the except. So again, the point here is you will bypass this part and it will come in here. So let's go ahead and put a semicolon and see if that goes through. And again, the type does matter, and you have to make sure it's the right type. So did you notice now, this blew up, so you went in here, that printed the result, and in turn blew up, so you go into the next exceptionally. So what's the moral of the story? The moral of the story here is, you have a data channel, and you have a error channel. When a data is generated in a data channel, what are you going to do? You take the data, x1, and you convert it or transform it x2 and x3, and you keep on going this way as much as you want to. Or you get an error. When you get an error, you can blow it up even further, and you can take this other error and another error and another error, and you can keep on going. Or at any given time, you can go from the data channel down to the error channel this way. Or at any time, you can go from the error channel up to the data channel. So you can take these kind of path back and forth. So you have data, oops, something went wrong, come to the left track, error, I'm going to recover, go back and process the data, and you can build this pipeline. That's your chain you are building. So it's important to understand the behavior of these exception processing blocks. You need to blow up if you want to propagate the error, if you haven't really handled it, or you want to return a recovered value, or both, depending on your input conditions. You may, based on runtime, you say, oh, you know what, I was actually able to recover from this, so I'll give you a healthy data to process, or no, this is completely messed up beyond repair, I can't help it, I'm going to just blow up and be done with it. So you can do that as well. So that's all great so far, but there's one problem in Java 8, and that is when you start a completable future. Let's go back to this code example right here. I'm going to return a value of 2. Well, that's all right. But this is generate, and I could do other operations also. And what does this do? It's going to say then accept, and then exceptionally, then apply and then accept, and print the result right here. That's all wonderful. And if the data returned is 2, it's going to take the 2, add 2 to it, and print it. That's also really beautiful. But I run this code right now, and what does it do? It printed 4. However, if I go back to this generate, what if this generate says sleep dot, let's say sleep, 10-second delay. So this guy is going to take a lot of time to compute. Now remember one thing, this may not be a 10-second delay. What if this is going to be delayed for ever? In this example, of course, you're calling it to be done, right? Well, what if you are not doing a generate up here? What if you took the completable future, gave it to some other function, it is going to call complete on you? What if that complete call never comes through after a very long time? What's going to happen then? Well, if you run this little example here, you will notice that it immediately said, I'm done. Well, that was kind of a little lucky, but we didn't process the data. But eventually we want to process the data. How long am I going to wait for that piece of data to finish? Or you may want to know that a task you set out to run was never actually completed, and you may want to do something about it. Unfortunately, in Java 8, there is no elegant way to do it. You can call get, and we know we don't really like get. So don't bother about calling get. So what should I do? How do I know this has taken way too long? There is one rule we have to follow both in life and in programming. Never do anything without a timeout. I mean, as an example, let's say you decide you want to find the perfect love. A smart person will never wait indefinitely to find a perfect love, because that's the best way to get old and die alone. So you start finding a perfect love, but you always put a timeout and say, you know what, I'm going to settle down. It's not going to work out. That's usually my opinion about life, right? You always time out on these things in life. And in programming too. You don't wait forever for something to happen. So that's exactly the point here. You just start out and say, I'm going to give you some time. If you don't finish in time, I'm moving on. How do you do that here? Well, thankfully, they introduced that in Java 9. So Java 9 now has two functions which are very useful. The first function that's very useful is a function to bail out if something doesn't happen in a certain duration of time. So for example, in this case, what you could do is you could take this completable future, let's put that into a variable. Completable future of integer, we'll call it as future right here. So this future, I'm going to then tie these operations to this future right here. So this guy is waiting for that to finish. And I'm going to go ahead and say, let's say sleep. How much time am I going to wait to sleep here? Let's say about 20 seconds. But in the 20 seconds, I want this to really finish, but that's going to take about 10 seconds to run. That's a total of 20 seconds to finish. I don't want to wait that long at all. That's too much time waiting. So what am I going to do? Well, what I'll do here is we'll go back to this code and say, well, I'm going to give it a little timeout. So future dot and complete on timeout. So we can tell him, I want you to wait a little long, but at that point, I just want you to complete if you haven't finished in that duration of time. So if the time expires, do me a favor, please, complete it for you. I mean, we do this in life, right? Hey, I'm waiting for this. If they call you, take care of the call. If they don't call you, do this work for me and go home. So you want to put a termination on this at a certain duration of time. So in this example, what am I going to do? Remember that guy is returning a 2. I'm going to return a 77, comma. Let's give it, let's say 2 seconds. And I'm going to say 2, comma, time unit dot seconds. So I'm asking it to wait for 2 seconds and complete at that time if the task is not completed by the duration. Oh, well, what would that do in this case? So when I run this, 2 seconds goes by. Notice I got a 79. And the reason I got a 79 is this guy said, hey, you know what? You told me to wait for 2 seconds. Nothing happened. So I took the decision, and boom, here's your result. Let's move on. So basically, that's what you're doing, right? I'm going to not wait forever. I'm going to settle in for this value at that time. Well, that's great so far. This is Java 9, by the way, not Java 8. So this is a welcome change in the addition in the language. That's really nice. However, what if this is going to finish before that duration? So if I go back here and say, this is going to take a 1 second delay, not a 10-second delay. Well, remember, this is 2 seconds. Now when I go back and run this little example, the value 2 propagates to 4, and the timeout doesn't really do anything. Well, the reason for that is when a completable future has either completed or canceled, you can never complete it afterwards. So that's pretty safe. But I don't want the data. I want to prematurely kill this if it's taking too long. What can I do for that? That's even better. You can just go here and say .r exceptionally. And you can specify in here a timeout. You can say 2 comma time unit dot seconds. So this says, you know what? I'm going to be patient for 2 seconds. If in 2 seconds you finish up your job, either you complete or you cancel. If you don't finish in 2 seconds, I am going to blow up. That's what this says. So this will begin to blow up and send a cancel exception to propagate through. Let's see if that's actually working. So I go back here. Remember that the code is pretty fast at this point. Oh, let's see. What is it complaining about? In this case, of course, so R, pardon, I'm having a wrong call in here. So this is telling us cannot find the symbol. This is not R exceptionally. This is going to be R timeout exceptionally, I think. I can't remember the word. Somebody can maybe tell me what the method call is that is in Java 9. So a little exercise for you. I'll make an asynchronous call to you, and you can come back with a callable future. So we're going to make the call to this and say that when this blows up, it's an OR function that's going to give you the result back to you and tell you what the result is. So that's what you're saying. Come back and blow this up at that particular time. Anyone knows the answer? Or on timeout, or timeout, thank you. So or timeout, thank you, excellent. So what is this going to do now? When I run this code, it is going to take the time. Hey, it finished, so that has no consequence. On the other hand, if it doesn't finish, what am I going to do? Well, let's make that a 10-second delay in this case. Well, that's of course going to blow up at the end of 2 seconds. So if I go back and run this little code now, 2 seconds later, it's going to propagate timeout exception, and that propagates through the system using the exception chaining. The ideas we discussed earlier are still the same. The exception is going to propagate through and give you the result back, and that's the way it's going to work. So you can also deal with this failure on timeout very nicely also. What I want to talk about next is 2 really nice and charming functions where we can bring completable futures together. This is very useful when you have multiple asynchronous tasks that you want to run, but you want to bring them together and do some operations with it. So let's talk about combine, and then we'll talk about compose. The names are kind of so similar, right? Combine, compose, or what does it mean? Well, let's understand what combine and compose mean. Combine is really easy to think about. You have a completable future. You have another completable future. You want to take the results of those two and combine them. So when one succeeds, and the other succeeds, you want to take them and combine them together. Let's understand how to do this with a little example here. So to understand this one, let's take a slightly different example here. Let's just mark this out. So I'm going to say public static, and in this case, we'll say int. We'll call it as get stock price. I'm not going to really get the real stock price, but in this case, I'll take a ticker, and we will say int. Well, that's good enough. Let's say int number of shares. So I want to take the number of shares, and I want to do some computation for the stock price. So in this case, I'll return. So what do I want to return? Well, I'm going to say in here, if we'll first of all define a price. So we'll say int price is equal to, let's say 1,000. If ticker, not ticket, ticker, if the ticker symbol is going to be equals to, let's say, Google, we will say price is equal to 500, for example. So we have these two prices, and I'm going to return, let's say, number of shares times the price. So I'm going to return 1,000 or 500, depending on what the share price is. That should be fairly easy to work with. Now what I will do here is, I want to do this, well, let's take baby steps on this. I want to compute the price for Google. How do I compute the price for Google? Well, I want to do this asynchronously. So CompletableFuture integer, we'll call it as goog is equal to, and this is going to become CompletableFuture dot supply async, and this is going to take the sample. Well, this is going to be sample supplier, isn't it? So this is going to fire up the call to the get stock price for Google. So there's the goog, and finally, let's say in this case, I want to provide, let's just say 1 stock. So I want to know what this is going to return to me. Well, obviously, this is running asynchronously. So I can say goog dot then accept And what am I going to accept at this point? The value, and I'm going to print the value given to me, right? So very simple example here. What is this? What do we expect? Well, the stock number of shares is 1. Google price is 500. So this better print 500 when everything is said and done, isn't it? That's what I'm expecting. So no surprise there. Let's do one more thing. Let's go back here and say, I want to now create, let's say, AMZN. In this case, I'm going to say AMZN. Well, we know this is not going to be 500, but it's going to be 1,000. Again, I'll keep things really simple by sending a value of 1. We don't have to do much math. So if I replace this with returning the value for Amazon, I can then put this here and say AMZN, then print the value. When I run this code, that's 500 and 1,000. So no surprise there also. So we got 2 asynchronous jobs running. They can take some time to run. When they are done, we get the result back. We can celebrate that. But I want to know my total net asset, if I own the stocks for both. What is going to be the value? Well, you know, I can take this value from here. I can take this value from here. I can do the math. But life is a little more complicated. This value is coming in inside this lambda. How do we get this value out of this lambda? That's going to get really messy. We create global variables, and you know, nobody is going to be our friend when we go that route. So what can we do to make this a little more charming? Enter combine. I want to combine the result of these 2 operations together. So what am I going to do? See if this makes sense. I'm going to say, first of all, goog.combine. And I'm going to provide the Amazon. So this says, when Google completes, wait for Amazon to complete. When both Google and Amazon complete, then I want you to take those 2 results and I want to combine them. And what am I going to combine them with? We could say Google price and then Amazon price, and then we could perform a total of Google plus Amazon price. But the beauty of this is, I don't want to do the output right here. Remember one principle of programming, the software should be cohesive. You don't want to put too much code into one place, then the code becomes uncohesive, hard to maintain. So you keep it cohesive. So this only performs a transformation. And the beauty is, the result of this transformation is a new completable future which contains that data which has been totaled up. So then what we can do here is we can say dot then accept. And I can now say, given the value, go ahead and print the value. So in this example, you know that you can also do then apply. You can perform a map and transformation further if you want to. So you can build up a lot of these things along the way nicely. So what is this going to do? It takes the Google's price and Amazon price, waits for them to complete, and when they finish, it takes those 2 values and perform the little math you want to do, arithmetic you want to do. In this case, I'm just adding those 2. Well, the result is, one was 500, the other was 1,000. So the result should be a 1,500 if everything went well. Oh, let's see what just happened here. Method combine says variable Google of type CompletableFuture cannot find the symbol. Yeah, what's the problem here? I want to combine these 2 guys together. So this is the Google's combine method. Apparently the combine doesn't exist on this. Let's try CompletableFuture.combine. Let's see if it's able to take these 2 values here. So this is Goog. Otherwise, we'll have to look up the doc to find out. My brain doesn't hold that. So what is this going to do? It's going to take these 2 results and combine them together to produce the results. And obviously, that's wrong also. Does anyone see the combine method over there?
The method name is then combine.
Then combine. Thank you. So the combine operation. Thanks for waking me up. So right there, we're then combining that together and producing that result over there. So this is going to just do the math and return the result for us. Hey, that's awesome. We got the 1,500. But of course, I intentionally gave silly names for these methods, these variables. And we often do, right? Because we don't care about those names. If we don't care about those names, don't give them variable names that are ugly. Instead, remove them. So what I would do is I'll say integer sum right here and use a method reference and just do the job. And that's a lot better way to write this than to actually go back and provide silly names. You could, of course, give Google stock and Amazon stock or Google value, Amazon value. That's perfectly fine. Or you can just use a method reference as well. So we can see that you say you took the Google and you combined. What's going to happen if it takes a little longer to finish? So to understand this, let's put a sleep over here. And in this case, let's say I'm going to give it about 20 seconds to finish up. Well, I'll go back here to this code. And in here, we'll just delay this just a little bit. Well, this is coming from the supplier, so we can take the luxury to do that. So let's say sleep over here. And let's go ahead and say this is going to become a value. How about saying this price itself? So I'll sleep for a second or half a second, maybe times 2 over here. So 2 seconds delay. Well, as you would expect, it's going to wait for the result to show up before it can perform the job. So that is perfectly fine. So it's going to wait for those two to resolve. And you know that they are resolving at a different time because of the sleep. And that works just perfectly fine as well, as we can see. But then, what in the world is compose? Well, before we talk about compose, let's step back and talk about something a little different, if you will. When you deal with streams, if you will, let's talk about streams. In the case of a stream-based programming, even though what we're talking about is not related to stream, this helps a little bit. Let's say you have a function f1, where it takes an object and returns another object. Well, a function takes an object, returns an object. For example, I could say, given a person, I want their first name. Well, that's a pretty simple function. You have a person, which is an object, and the name is an object. But I don't want a person's name. I want everyone's name who is in this room. You know what we can do for that? We can say collection.map, or stream, which is a collection in this discussion. And then I can put F1. What will this do? Well, this takes a collection and it returns, at this point, a collection. So that's the transformation we have on our hands. So map works really well for this operation. What if I have a function F2, where it takes an object, but it returns a collection of objects? For example, given a person, I want all their email addresses. Not just one email address, but all their email addresses. Somebody may have none, somebody may have 1, somebody may have 7, somebody may have 20, but I want all of them. Unfortunately, if I say collection.mapf2, we now go from a collection to a collection of objects. May not be what we want. Maybe sometimes that's what we want, but maybe that's not what we want. So what is the answer for this in functional programming? We don't use map for this. We use collection.flatMap of F2. This will take a collection and return a collection. So moral of the story, if you want to use a function that is a one-to-one function, use a map. If you have a one-to-many function, but you want to go from a collection to a collection, not a collection to a collection of collection, then use a flat map. So here is another way to think about it. Does your function produce an object, or does your function produce a collection itself? We can apply the same reasoning now on CompletableFuture. Let's go back to this code. Did you notice what getStockPrice returns? GetStockPrice is returning an object, a primitive in this case, integer, whatever object it could be returning. So in this example, I can take the goog, and what I can do here is I can say, given this goog, I can then put a little call that says dot, then accept, and then I can say in this case, what am I going to say here? Given a value, I want to output the value. Well, that would work really well because the getStockPrice is returning an object, as you can see right here. And so when you run this, the then accept will simply take that value and transform it to print it, or then apply will do the transformation. So that will work really well for that particular case. However, there are times when you may want to really implement a method which is truly asynchronous. So in this case, let's say the method we have here, which is the what is the method we have here, which is the get stock price. What if get stock price were to return to us not a nice little object or primitive? What if that were to return a completable future itself? So in this case, I'm going to say completable future of integer. So when I call the get stock price with a ticker symbol and a net price, it says, I'm not going to give you an immediate response. I'll get back to you. So I'm going to give you back a completable future, and I'll take my time, sweet time, to compute and get you the result back to you. So in this example, the way I could do this is I could say, return new completable future, and this is going to take a supplier, and I could take my sweet time within the supplier to actually do the work and return the response back later. So this could be returning a completable future, and this could be taking its own sweet time in another thread to do the work. Unfortunately, though, if I create a supplier, well, you could argue, why can't you just say get stock price and then call then accept on it? Sure. But remember, when we do the combine, if what you're getting is another completable future, or in the middle of your transformation, what if your function is yielding something else? So to understand this, let's step back for a minute. Let's say we have a string on our hand. So the string, we'll call it we'll say list of string. We'll call it symbols is equal to list of, let's say, Google and Amazon. So I have a couple of different things, right? MZN. But what I have is a completable future dot supply async, and this is going to return to me symbols dot get of some value 0, let's say. Well, now what just happened? This is giving me a completable future of a symbol I'm going to work with. Now I can say over here, dot then accept, given a symbol, well, then apply rather, given a symbol, I could say get stock price for the symbol and maybe some number of shares. But earlier, remember, get stock price was returning a price. This would work really well. But now, get stock price is not returning a price. It is returning a completable future itself. We're in kind of a pickle here, right? Because when this guy returns a completable future, what is the result of then apply? The result of then apply is not completable future of integer, but it is completable future of integer. Yikes. That's not what we quite wanted. Notice how we are in the same kind of a situation as the flat map situation. So the question is there an equivalent of flat map available for us in the completable future scenario? Well, remember, then accept is kind of like for each, then apply is kind of like map. So something is like a flat map. It's got to be something like that, right? In other words, something should say, give me a function that returns a value, then you can use then apply, but give me a function that returns a completable future, then I will work with it. Now you know the rest of the story. That's basically what compose is all about. So compose says, if your function returns another completable future, then quietly remove that inner completable future and then pass the integer to me. So going back here, then apply is not going to be fun, then compose. And what am I going to do here? So let's step back for a second. I mentioned this is returning. What is this returning? This output is completable future of integer. If I say dot then compose of symbol over here and arrow get stock price of symbol comma 2, then the result of this is completable future of integer. So in other words, this is going to take the inner completable future, wait for it to complete, and then take the result of that and propagate through your chain at that point. So that is basically, so that is why I see this as the then accept is like for each in streams, then apply is like map in this, and then the then compose is really like your flat map in the case of a stream. So this is a nice way to think about how these three are related. In my mind, I always think of these transformations. And when I think about it as a transformation, it becomes a lot easier for me to work with in terms of how these are going to combine together and function. And so this is the equivalent of how these things work together and compose really well. And that can be a very powerful way to put things together. So what we saw here was the completable future. Well, now we can take this and do divide and conquer operations. So when you put a little job on me, I can either solve it right now, or I can break it down into other completable future, and the compose gives me a nice way to return to you a completable future, which will then go subdivide the problem and work with more things, and then we can put them all back together. So to summarize what we talked about how we can solve problems using parallel collections, or we can use a divide and conquer. And we saw how parallel collections are useful with parallel streams. We talked about the pros and cons of using it. We then talked about how we can use completable futures. Keep in mind they are just promises of the JavaScript world living within Java. And the one difference between those two is streams of data in the case of stream versus one success or failure are not yet resolved through completable future. If you want to download and play with the examples I've provided here, you should be able to download them as of tomorrow from my website. And when you click on the downloads link, it should be fairly at the top tomorrow or later. And then you should be able to download and play with these examples. I hope you found that useful. Thank you.